So, hello again. We're
Hello.
back. Hello, everybody. We're back for the second day of this year's Software-Defined Radio Academy, and for technical reasons, we had to postpone one talk. The speaker here now is Adrian Muschak in the picture below me.
Hey.
Hello, Adrian. Thanks for coming in
Hello.
today. And I would like to present Adrian to you. So Adrian is a Romanian amateur radio operator holding the call sign Yankee Oscar 8 Romeo Zulu Zulu, and is a Linux developer, a Linux software developer, and he's been interested in software-defined radio ever since he discovered GNU Radio around 2007, quite some time ago. These days, most of his radio contacts are made using his own SDR application described in this talk, and he's here to share his experiences. So we're going to play the pre-recorded talk. For the video team, please go ahead.
Hi, everyone. My name is Adrian, and it's very nice being back here at the Software Defined Radio Academy 2021. Today, I would like to talk about the GNU Linux multi-mode SDR transceiver application using GNU Radio and having voice over IP functionality built in. So as far as a brief introduction of the QRadio Link application, it is a small application which I have developed as a multi-mode SDR transceiver for Linux. It is free software and it's using the GNU Radio C++ API for digital signal processing. User interface, which you can see in the picture on the right, is written in Qt. It is very similar to GPRX. It basically uses the same graphical widgets which were kindly granted the permission to use them by Alex Chete, the author of GPRX. The application is mainly focused on digital voice communication as an amateur radio experimentation tool. It allows communication with digital voice nodes. It also supports analog voice communication with FM, AM, SSB, and it also has a video mode and an IP protocol data transmission mode. One of the core features of the application is that it bridges audio from analog digital radio, basically the SDR, towards the IP network. This allows the radio to be connected to various desktop or LTE mobile terminals, and also other radio sites which are using QRadio Link to transmit or receive signals. The development cycle is aligned with Debian Bullseye, so this means that you can expect any Linux distribution which is derived from Debian Bullseye will be able to build and run the application. It is also using some versions of the libraries which are listed below, in case you are interested. Now, a little something about the technical features which are built into QRadio. First of all, as an application, it is compatible with devices supported by GNU Radio Osmo SDR, and also devices supported by SOPI SDR, the other main device compatibility layers. Among others, the SRP, the ALGA, and Pluto, which is commonly known as the Pluto SDR, the Line SDR, the RTL SDR, the Blade RF, the Hack RF, and other devices which may or not be the supported as well as the ones listed here. It has semi-duplex and full duplex operating modes, depending on operator selection, of course. It also has voice activation for external applications like WSJTX, which I have presented last year also here at the Software Defined Radio Academy. The application allows transmit-receive switching and supports various external amplifiers and filter chains by using USB relay boards, which have the FTDI chipset on board. So it will be able to control up to 8 relays from this type of USB relay boards. The operation can work with in split mode and with repeater mode. It also allows mixed operation, which means that we can transmit digital voice signals and receive analog signals, and also vice versa, receive digital and transmit analog, either in semi-duplex or in full duplex mode. It also has support for audio recording using the free lossless audio codec. It has very basic remote control interface, which can be accessed either via Telnet or via mumble text messages. It has memory channels, very basic headless operation mode, which means it doesn't have graphical user interface. And it can also operate in a repeater mode, which means that it can retransmit any signal which it receives, but only in full duplex. So the software-defined radio must have the duplex capability. It also has support for forward error correction in digital voice modes, video, and IP protocol transmission using convolutional encoding, which is a very simple, basic forward error correction, but it's adequate for most purposes. It can work with multiple sample rates from 1 megasample per second towards 30 megasample per second for both receiving and transmitting modes. Like I said, one of the core features is voice over IP radio bridging using the Opus audio codec and the Mumble voice over IP protocol. And as far as compatibility with various Linux sound systems, it uses the Qt audio API and also the Qt video API, which makes it compatible with a wider array of Linux sound systems like Pulse Audio, ALSA, and also various types of video devices which are supported on Linux. And now moving on to the digital signals which can be transmitted and also received with the application. It can operate with digital voice and text data by using the FreeDV modems. I'm sure most of you are aware of FreeDV as quite a famous digital voice mode, which was created by David Rowe, VK5GR. And this SDR transceiver also can transmit standalone codec 2 with various modems. You can see here, for example, waveforms for DQPSK, transmitting codec 2 and transmitting Opus digital voice, and BPSK, binary phase shifting, phase shift keying, and also frequency shift keying, either to PSK and 4FSK. Digital voice is using codec 2, like I said, at 1,400 bits per second, or for a better quality, let's say, sort of a wideband audio mode, it can use the Opus codec at 9,400 bits per second. Of course, this means that the signal will have a larger bandwidth than, let's say, one of the FreeBD waveforms, which are depicted here in these images. As far as FreeBD, it supports FreeBD 1600, FreeBD 700C, 700B, and 800XA, which are, most of you are probably familiar with these modes, especially 700B, which is quite popular for shortwave communications. Since the application can also transmit analog signals, this is a very brief list of the analog waveforms which it supports. First of all, FM mode in a channel of 12.5 kilohertz. Also narrow FM at 6.25 kilohertz. It has support for coded tone, coded squelch encoders and decoders, which are blocks in the GNU radio. The SSB mode, it is developed using the continuous envelope SSB transmitter, which is a GNU radio out-of-tree module that was developed by Ron Economos, W6RZ. This mode has some very interesting features because it ensures that it does not exceed certain levels, causing clipping and signal splatter, which is very useful for SSB. It also supports the IM amplitude modulation mode. This is a very basic implementation. It's not very common in amateur radio. And it can also receive wideband FM for broadcast radio reception. In order to operate on FM repeaters, it has configurable repeater shift. So you can define your own repeater shift, and in semi-duplex mode, it will be able to operate on repeaters by changing the transmit frequency as the push-to-talk button is pressed. The semi-duplex mode is standard, which means that you have to press push-to-talk in order to be able to transmit the signal. But it can also operate in full duplex mode, which means that reception of the signal is not cut out. You can either monitor your own transmission or serve as a very basic repeater in this mode, because the application will just forward any signal it has received into the transmit port of the SDR. Another feature is the audio compressor. This is something that is very useful for the SSB mode, and is also usable for the digital voice modes, because the audio compressor can operate also both on input and on output. Other features are audible end of transmission notification for FM modes and audible timeout timer notification, which can be configured with a variable amount of time to either cut you out from transmission or to give out this audible notification in order to let you know you've exceeded your time on the air. Moving on, the core feature of QRadio Link is the voice over IP bridging interface. This bridging interface is designed so you can link your software-defined radio with an IP network and be able to communicate between radio nodes using the IP network and a server which serves to kind of like a reflector in order to push the audio samples towards all the clients which are connected. This can connect the transceiver with either desktop or LTE mobile clients on the same server, and obviously on the same logical channel. It has a client-server star architecture, which is depicted here in the picture on the right. It has this core server, which operates on the IP network. It can operate either on the same computer as Pure Radio Link operates, or it can be on a completely different computer. But this server allows connecting desktop clients, which there exists a variety of clients for the Mumble protocol, either desktop or possibly mobile. So you can use this voice over IP protocol with mobile phones, LTE mobile clients. There is server-side logical channelization, which means that users can be divided into talk groups, and the user can join or leave a talk group as he pleases. In order to transmit the voice over the network, the Mumble voice over IP protocol with Opus as an audio codec is used. This protocol, besides the audio frame, also has in-band signaling. So you can transmit text messages and also various commands which operate on the server or on other clients. For the radio signal, there is no call setup overhead, which means that once a radio signal has been received, audio is almost instantly propagated over the network, and PTT audio is activated on the other side. So there is very little overhead, no call setup, no time required to make a connection, no dialing involved. Latency is brought about mainly by network latencies, which can have significant values in case of LTE networks, for example. Also transcoding, because if let's say one of the software-defined radios is transmitting and receiving a digital signal, there might be some transcoding required from, let's say, codec 2 towards Opus, or from an analog signal waveform towards Opus packets, which are then sent over the network. Digital software processing also adds some latency, which may not be very small. This is latency which cannot be overcome. But the overall figure is around 400 to 600 milliseconds for an LTE client round trip, which means that by using a mobile phone, I am able to remotely operate my SDR transceiver, receiving and transmitting using push-to-talk on the LTE client, and have a delay of around half a second for the complete round trip. This architecture also allows radio server-to-radio network bridges, which means that you can have two radio sites in two separate locations, and one of the radio sites will receive a signal retransmitted over the network to the other radio site, which will then rebroadcast the signal. And this is valid for all the clients connected to the same talk group will also retransmit the same signal. The audio is bidirectional duplex, and the IP bitrate is flexible, so it can be configured within some values inside the application. Another feature of Pure Radio Link is the video transmission mode, which is a very simple implementation. It doesn't try to compete with DVD standards. It has around 10 frames per second. The video frames are transmitted directly after capturing and encoded using the JPEG video codec. Voice is also transmitted and is encoded with the Opus audio codec at 9,400 bits per second with a constant bitrate. Audio frames are around 100 milliseconds long. The modem which is used to transmit the video signal is 125 kilosymbols per second DQPSK modem, which fits in a channel of 500 kilohertz, and it has half-rate convolutional code for their operation. Video frames are also checksummed in order to avoid spurious decodes and errors which might creep up in transmission. And the capture backend is Qt Video, which requires some GStreamer plugins, and it uses the system default video device, which is the one which is detected by GStreamer backend. This pretty much completes the description of curating and the feature of this small application, which I wrote. And in the end, I'd like to thank a few people because writing this software and experimenting with it would not have been possible without them. Nathan Bottoms, A4HS, is the Debian New Radio and 3DV integration developer, and is also doing the maintenance for these software packages. Alexander Chete, Oscar Zulu 9, Alpha Echo Charlie, has kindly granted me permission to use some GPRX widgets and some code in order to avoid duplication in the application. Also, Daniel Esteves, EA4GPZ, his open research and his publications were used in the development of the application. David Rowe, the author of Codec 2 3DV, and also has given me very valuable DSP advice. Marcus Miller, he has provided me with the GNU Radio architecture and DSP advice. Stephen Sostrom, he has been testing and providing documentation for Raspberry Pi OS integration. And of course, the GNU Radio and amateur radio communities, including everybody who participated in testing, bug submissions, feature suggestions for this application. If you want to read more about this topic, you can head over to the website at http://curadolink.org, and the code is available at GitHub at Curadolink project. Now, bear in mind this application is currently not considered very stable. It hasn't reached yet version 1, so there are still, I think, plenty of bugs or issues to solve. But it has been suitable for me in the last years or so. I have been using it almost exclusively to operate in amateur radio bands. And this pretty much completes my presentation. Thank you very much for watching, and hope to talk to you later. Bye-bye.
So, Adrian, thank you very much for this very insightful talk on your own application. Very, very interesting. That's particularly interesting because many people are actually thinking about having kind of a remote station. That's a very common discussion since we're thinking of high noise levels, particularly in big cities. So the question for many people is to place a receiver outside in the countryside, like we're here, right? I didn't tell you. I think I didn't tell you where we are right now. We're in the middle of nowhere, north of Munich, out in the countryside, and this is actually a very nice environment. When I look outside the window, there are cornfields. Of course, the window is blinded now, so that we don't get stray light. But out here, we actually have a very, very silent, high-frequency environment, and this is what many people want to have. And I mean, I tend to say for the legal limit, or a kilowatt in the city, for the legal limit in the city for transmitting, the power amplifier doesn't care for the noise level. It doesn't matter. But if you have a receiver and the noise floor is very high because of many power supplies around there, that's really a big problem in the city. So many people are really interested in having a receiver out in the countryside and being able to use it interactively and possibly also to transmit. And so this is why your developments are really very, very interesting for sure to many people. So there have been a couple of questions here in the chat, and Michael, if you want to raise your own question.
The first question is an icebreaker. Is there any recommendation how to put the 9,400 bits per second from the Opus codec into a shortwave radio channel of 2.5 kilohertz. Are there any ideas, or how could it be used for shortwave radio? Couldn't it? Or isn't
I,
it
th-
only 3dB?
I think Daniel Esteves can actually answer that question better than me because he's been working on 16 or 32 amplitude PSK modulated mode for the Quebec Oscar 100 satellite. So he would actually put an even higher bitrate over the channel than this is the modem I used was just for testing the Opus codec for a radio channel. Basically directly forwarding the audio frames coming in from the voice or IP connection towards a radio channel, which is similar in bandwidth as FM, regular FM modulation. But yeah, there are definitely ways to fit that into a SSB bandwidth type channel. And like I said, Daniel Esteves is actually working on that. Hopefully, he will give us talk about that very interesting high bitrate mode for Quebec Oscar 100.
Okay, thank
Yeah.
you.
Okay. And Bob, F4G Golf Sierra Whiskey has been asking if the software can be operated on a touch screen only device. So if you have a device with only a touch screen, is that possible, or do you need a mouse and a keyboard?
In the first time I began working on the software, I actually managed to run it on my mobile phone, and the controls were designed so they were easier operated just by using the finger on the mobile phone's touchscreen. But as it evolved, I kind of gave up on that idea because there are currently some open source projects, like for example the KDE Plasma project, which is supposed to give a very nice touchscreen interface to be used on mobile phones and tablets. And in order to make it make the usability better for the application on such interfaces as touchscreen, I would say would need to implement the custom KDE controls. KDE is a desktop environment for Linux. If you're not familiar with that, it's like an alternative to GNOME and LXDE and more desktop environments. But KDE Plasma itself is focused especially on mobile devices. Hope that answers the question.
Okay, very interesting. So, Jean-Michel, do you have any questions?
I would certainly second your consideration about remote control, which is certainly the most attractive aspect of this presentation. And following Barry Durden's presentation yesterday on ZeroMQ streaming, I find it interesting here to see all the protocols that have been implemented for this remote control. So certainly a very interesting development on top of New Radio use here as a library for as the base of this software. So thank you for his presentation. Yes.
Sure.
Well, I also have a short question, which is about timing once again. So we've seen the Kiwi SDR, which is based on OpenWebRX, and the Kiwi SDR has a very interesting feature, which is time difference of arrival, location finding, and the Kiwi works with a GPS receiver chip on the set-top board. So, would you think this is an interesting additional development in the future, maybe to distribute? I mean, it's great if you're operating this for yourself. That's perfect. But I guess what you're interested in also is that many other people are using it. So if you're building kind of a network of those devices, so that you can use the network again in a sense of combining different signals and analyzing different signals against each other, creating correlations. Do you think creating a common time base is an interesting path of development?
Yes, it could be. One of the reasons, one of the inspirations for the voice over IP support has been a nationwide radio over IP network, which is implemented here in Romania. It's called the Rolink network. It's basically a single calling channel on VHF in UHF frequencies. It's a project spearheaded by Cătălin Yankee Oscar 7 Golf Quebec Zulu. And it's got over 200 repeater and simplex nodes operated. So it's all IP network-based infrastructure, and basically by activating a single node or repeater, it will open all the nodes in the country, and you will be heard all over the country just by using a portable small size terminal. But it's got some problems like peak usage. So basically, because it's a single voice channel, on peak capacity times, let's say it's a bit crowded. So that's like an opportunity for logical channel separation and perhaps using a different multiplex access. So basically, I'm doing some investigation of using also, using SDR for multiplexing multiple logical channels, and also maybe using digital voice codecs over radio. But your idea about so you can compare the times of arrival. Obviously at the device, because you also have to multiplex the IP streams together, and IP streams will have their own latency. But you can basically add metadata to the streams which are received by the device, add the metadata, and then when you're doing the demultiplexing at the remote station, then you can compare the times of arrival. So yeah, that's an interesting idea. Never occurred to me that it could be used for that. I'll think about your use case. It sounds. What exactly purpose would you have that in mind? Like measuring, I don't know, the path, multipath taken by signals, or?
Yeah, these multipath signals, where they come from, that's interesting. Analyzing the spectrum, where a station is interesting. Well, intruders to our bands find where they are. That's also an interesting application. There are many interesting things. I mean, very often the question is, where is a station? Where does a station come from? So
I think you can do that as long as you add metadata at the receiver and then multiplex. You send the IP stream to a central location, and then you demultiplex and compare the metadata that was added by the receiver when the stream sample was first captured. So yeah, it's definitely possible. There are some latencies involved because my application unfortunately uses a lot of buffers. It's an engineering trade-off between having less audio interruptions and more buffering. Basically, adds quite a bit of latency on the order of maybe 100 to 100 milliseconds. But it's doable what you're suggesting, as long as the signal, the path delay of the signal is more than that. I'll think about your use case. It's an interesting use case. It never occurred to me.
Okay, excellent. So we would have two more questions here in the chat, but we need to continue. We have the next talk right in the queue. Thank you very much, Adrian, for this interesting talk and the nice discussion. And we'll have you in the panel later on, so we can go deeper into these questions in the panel. Okay, thank you very much. The next speaker, thank you. The next speaker here is Sriraj Rajendran. Hello, Sriraj.
Hey, hello.
Good to have you here.
I'm happy to say.
So the audience, I'm going to present Sriraj to you. He joined the Elucidator Lab series in June 2021, a very short time ago. As a data scientist, he's involved in industrial research and development projects, enabling machine learning-based solutions addressing the needs of the Belgian industry. Sriraj is located in Belgium. Before joining Cirrus, Sriraj was a postdoctoral researcher at University of Leuven, and he obtained his PhD degree from KU Leuven, as you pronounce it, in electrical engineering, and he's a free and open source software enthusiast and has a few years of experience in industry as a digital signal processing engineer in the telecommunications sector. So, as we previously have done and as we're doing now, we have pre-recorded your contribution, and I would like to hand over control to our video team. Please, video team, play Sriraj's contribution.
Welcome to this talk on knowledge extraction from wireless spectrum data. I'm Sriraj Rajendran, and I'm a postdoc in the electrical engineering department of KU Leuven. The idea of today's talk is to give you an overview about why spectrum knowledge is important and how you can attain this spectrum knowledge on an large scale. I'll also give you an overview about wireless spectrum anomaly detection, how you can do anomaly detection from a large amount of data that is available. We'll also talk about signal classification. Once we identify some signals, once we have some signal, detect some signal, how we can classify these signals and how to use some of the deep learning models to do that. So previously in last year's SDRA, there were a few talks on cyclostationary analysis, deep learning based wireless signal classification. So I'll try to cover something extra beyond that. So let's start with why wireless spectrum knowledge is quite important. Instead of giving you the complete spectrum allocation and other rules, we'll try to go through a few solid scenarios where this is quite important. Let's think about an airport scenario where the location and status are updated through wireless channels, for instance, ADSB messages or other information that you send, that the flight send. Then think about like surveillance radars, ATC communication. All this communication is happening over the wireless channel, and jamming and spoofing on these wireless channels is quite common, and there are many papers which discusses these kind of attacks. Only in Belgium, like in 2019, there were around 23 reported radio interference issues from Belgian air traffic control. So this is it's quite important to know how the spectrum behaves in the aerospace bands. Telecom operators, they are trying to make their cells quite densified for high throughput requirements. Hence interference is also increasing. There are network outages. There are people deploying fake base stations using easily available SDRs these days. There are people deploying signal boosters, again, which affects the cell planning, and mobile wireless interference is one of the prominent interferences that is reported in Belgium in past few years. Consider ISM bands where interference and usage analysis is quite important. For instance, there are companies which make use of ISM bands for instance, parking lot meters and kind of things, and they would like to know what is the usage statistics of these ISM bands, how much interference is present, and how it behaves. Defense sector is a no-brainer. They will always like to classify the enemy signal, localize it, identify it, decode it, and so spectrum knowledge in that domain is also quite important. Again, for end users and amateurs, like they would like to know the Wi-Fi channel statistics, how much radiation is there in the some frequency bands, and all those use cases. So spectrum knowledge is quite important for a large variety of use cases, and it's one of the problems that we are trying to solve. So currently, how is it done in Belgium and other countries? Like we have a few fixed monitoring stations. In Belgium, I think there are 3 or 4 fixed monitoring stations, and there are a few mobile monitoring units also. Like these are vans that are equipped with SDRs and other high-end spectrum analyzers to see where from where the interference is happening. BAPT, which is a regulatory agency in Belgium, in last year, like in 2019, reported around 440 interference cases. Around 15,000 devices were seized. This includes devices, wireless devices, that comes through the customs also. And also there were around 500 monitoring visits based on the complaints that were raised. So normally they do it in a manual fashion. Like whenever there is an issue, someone logs a complaint, and based on the complaint, they go there with their, based on the priority, they go there with their van and with their equipments and try to do the analysis. So right now it's in a suboptimal manual way, which is now how it is happening right now. So we also tried to tackle this problem when I started with my PhD here in KLeuven. So our idea was to come up with some set of crowdsourced sensors and low-cost crowdsourced sensors, and try to get data from the spectrum and analyze it. So this is a project called ElectroSense, which was developed by the collaboration between various universities and research institutes. So ElectroSense is a non-profit organization. India Networks from Spain, Servo Systems from Germany, Armasus, and KLeuven. So ElectroSense consists of very low-cost sensors. Basically, they are Raspberry Pis with RTL SDRs connected to it, and which is connected to the internet. And it sends data to the backend, an ElectroSense backend, where we run various services like classification, anomaly detection, decoding, etc. Users can also get this spectrum visualization, spectrum usage statistics from the interface, and there are also some free decoders available to decode ADSB messages via AM radio, FM radio, and all kind of things. So if you're interested, you can go to electrosense.org, and all the source code for the sensor and other algorithms are also available on GitHub. So this is how we started collecting data to analyze wireless spectrum. And then the challenge was to extract knowledge from these collected data. So we'll first start with anomaly detection. So let's define what an anomaly is. So an anomaly can be anything. It's a user-specific issue. It can be jammers, can be anomalies. New transmitters appearing in a particular frequency band can be an anomaly. Transmitter parameter variations like power variations, frequency variations, etc. can be an anomaly. A transmitter behaving in an unusual transmission with an unusual transmission pattern can be an anomaly. So any of these can be an anomaly. Why is it challenging? It's because, like as I mentioned, the anomaly can be a wide variety of things, and manual labeling of all these things in different frequency bands is quite difficult because wireless spectrum usage is quite complex, and in particular, some frequency bands, the rules are different when compared to another band, and the rules change from country to country also. Upon that, like there are sensor variations. For instance, even with very close by sensors, there can be antenna variations. One antenna can be indoor and one can be outdoor, and they see different kind of signals. So in a supervised setups, it's quite difficult to manually label this data. And in an unsupervised setup, we can come up with a solution saying, okay, less frequent events are anomalous, which is a common way to do it. But again, it's not fully true in wireless scenario. For instance, if you consider an ISM band, a less frequent event like a car key wireless transmission is not an anomaly, but a pirate station that is transmitting for a few months that ends up in your data set can be an anomaly. So it's quite challenging in this sense. And our interest was to come up with a single anomaly detector for different frequency bands. So an anomaly detector should work across sensors and across various frequency bands. We should also get some insights to the anomaly, in which part of the spectrum it is happening and why is it happening. And we wanted to do to some extent fully unsupervised anomaly detection. So we started with electrosense data, try to detect anomalies using that. So we started with a data set where the anomalous behavior is quite low. We didn't do any explicit anomaly labeling, and no expert feature extraction is performed. So just to talk about the model, how the basic model works. The basic idea is similar to how kids learn. So consider you live in a city of dogs, and your kid only sees dogs. He or she learns a few features that helps him to identify these dogs. And suddenly a cat appears in the city, and because of the similarities, he thinks it's a dog. It's what he learned, but he thinks it's a dog, and for an external user, you can notice that the reconstruction error or the reproduction is quite bad. So from this, you can say whether it's an anomaly or not. This is a basic principle that we use in our models also. So we use autoencoder kind of deep learning models, which consist of an encoder and a decoder, which brings the actual data into some features and tries to reconstruct the actual input using the features. And then we train the model in a completely unsupervised fashion. So you can train this model based on the reconstruction laws, and whenever there is a huge reconstruction error, you can say that it's an anomaly. The good thing about these kind of models are you can also train them in a semi-supervised fashion, so that you can say that some of these things are not anomaly, or you can also train them to learn some specific features which help us to quantify the anomaly or understand why this anomaly is happening. So this is a basic idea, and this is our actual model. The model is called SAFE, and it's an adversarial autoencoder based model. I'm not going to the fine details of this adversarial autoencoder. It's a very famous structure which you can read about. So as I mentioned before, you have an encoder. We have an encoder and we have a decoder. We feed power spectral density data or spectrogram data as input to this model, and this is a reconstructed output. And the model is trained on the reconstruction laws. Along with that, we impose a few distributions on the features, and we also have some semi-supervised features such as the class variable that identifies the frequency band. And whenever there is a huge reconstruction error or variations from this the expected distribution, we say that it's an anomaly. So the model is also open source. You can find it on GitHub, and the details about the models are and some advanced models are available in these two papers. So let me show you a simple demo how it works. So what you see here is the spectrogram or PST input that is coming from an SDR, from a hack RF that is scanning 40 megahertz of the GSM spectrum. And below you see the anomalous region. So top is the GSM band, and below is the anomalous region. So you can see the new transmitter appear here in the band, and suddenly it detects it as an anomaly. So basically what the models learn is like the actual data distribution in a particular band, and whenever there is a variation from the actual distribution, it detects it as an anomaly. You can detect duty cycle variations to some extent, then out of band transmissions, etc., quite easily using this kind of models. And even if there is a jammer similar to this one, you can actually detect it quite well. So is this enough? So this is the first step that we took, but there were various other problems that needs to be solved. For instance, how to handle sensor variations. As I mentioned, even if the sensors are quite close, the signals that it sees might be quite different. For instance, like if you take two sensors in two different locations, and then if you check the FM bands, the transmissions might be different in different bands at different frequencies. Similarly, an anomaly is also user specific. Consider an example of a telecom scenario where they put a new base station. For them, that transmission is not an anomaly, but for a normal user, it should be considered as an anomaly. So it's also user dependent. So we try to answer questions like how you can incorporate user feedback to this framework, how to use this expert feedback across users and across sensors. I'm not going to the entire details of this model, but we have a complete framework to solve all these problems. And this framework works on the same principles that I mentioned before. Also, like, we include some kind of semi-supervision and use some traditional machine learning models, algorithms to tackle these problems. So you can find the entire framework there in this 2019 paper. Okay, so now we have some way to identify the anomalies. The next step is how to classify them. So previously, this was also a talk during last SDRA, like where the presenter presented cyclostationary based feature detection, and this kind of cyclostationary models were the conventional models that we used for wireless signal classification. Basically, it does some kind of similar to some kind of moment generation or correlation, and then try to find cyclic features from there. That's what these algorithms actually do. But right now, we are using deep learning models, which gives state-of-the-art performance. We have proposed a few deep learning models, and there are some other state-of-the-art models that performs quite well. The things the models that we propose should be robust against all the variations that we expect in wireless, like time shift variance, channel variations, symbol rate variations, and other parameter variations of the signal. This is quite challenging to achieve. So during the last year's talk, there was also deep learning based wireless signal classifiers. I will talk about some of the major issues with these kind of models, how it behaves, and why does it, and in what regions it doesn't perform really well. So one of the main issues of these kind of models is generalization. So these models work really well on the data it's trained for, but whenever there is a change in some of the parameters, the models fail miserably. So for instance, here on the right hand side, you can see the accuracy drop for 3 types of models, like ResNet, 1D CNN, and feature-based higher order cumulance-based models. So these are the state-of-the-art models, and whenever there is a change in the channel condition, for example, for instance, this is a section where the model is trained on AWGN channel and it moves to Rayleigh and Rising channel. You can see that the accuracy drops are quite high. The accuracy drops of the cumulant-based, feature-based models are quite low, but the actual accuracy of these models are also very low at low SNR conditions. So, so what I wanted to convey is, like, whenever there is an out of distribution data, the models fail. It's quite a problem in our case also with electrosense data and other data sets that we have. In order to give you some examples, let us consider the impact of upsampling. So what you see here is constellation diagrams of PPSK and QPSK signal. So on the left-hand side, these are the signals where the model is trained on. On the top, you see the conditions where the signals are tested on. So consider a BPSK signal, which is trained on AWGN channel with upsampling factor 8 and a sampling frequency 200 kilohertz. And again, the same parameter, the constellation looks good, and the features learned, which are shown by these lines and these dark points, it looks good and it's classified well, which is indicated by this green color. But if the upsampling frequency changes, the If the upsampling factor changes, you can see that the classification goes wrong. Even when you can clearly see like there is some, it's still a BPSK with some timing issue, and the model fails to see this. So this kind of intelligence or causal reasoning is still not present in our models right now. Right now, we try to solve this problem using transfer learning and spatial transformer networks. By transfer learning, we mean like we use a quite small percentage of data from the target domain dataset, or from the new domain, and try to use that to train your model. Or similarly, we use spatial transformer networks to generate new kind of data distribution from our actual dataset. This can improve your classification accuracy from 10 to 30%. As you can see here on the left, here is a model that is trained on an upsampling factor of 8 in 3 conditions: AWG, Rayleigh, and Bayesian. And you can see when the upsampling factor changes, the model accuracy drops. But if you use spatial transformer networks and transfer learning, you can withstand this reduction to some extent. This is not a perfect solution, but it looks quite good. So the accuracy is quite low, to 80%, because this is an average accuracy across SNRs from -20 dB to 20 dB, and for around 20 for a 20 class modulation dataset. So 80% is an average accuracy. So if you go to the higher SNR region, the accuracy is close to 90-95%. We also make use of this kind of deep learning models for combined detection and classification. In the sense, it's similar to the models that you see in the image domain, where there are multiple objects and in an image, and you try to detect all these images, draw squares between these around these images and around these objects, and try to classify them. We also have models that does that. So for instance, for a drone detection problem, we use this kind of YOLO kind of models for wireless signal detection and prediction at the same time. And the prediction accuracies are quite good for different numbers of drones. And you can see the F1 score here for very low SNR regions itself. It's quite good. So deep learning models and machine learning models are used quite well in all these scenarios, quite effectively. But again, it lacks a few intelligent things that we can easily recognize. So to conclude, data collection wise, with frameworks like ElectroSense and crowdsourced networks, we can collect really good spectrum data these days. We can, with the help of deep learning models, we can do anomaly detection quite well using unsupervised models. If you employ some kind of semi-supervision, we can improve the anomaly detection performance, and you can incorporate user feedback to these kind of networks. We can do quite fast signal classification these days using deep learning models from a few samples. In the sense hundreds of samples, you can classify the signal fast. And similarly, a lot of machine learning accelerators are available these days, like Google Coral. So you can actually put these models on the edge itself and do the classification there. Again, these models suffer from model generalization issues and causal learning issues because some things that we can identify quite easily as humans, still the models are not able to do that, and we have to induce these kind of causal learning to these models. So once we have this kind of knowledge, we make use of this knowledge for improving wireless transmission itself. For instance, we use these models and spectrum data to do transmission prediction and interference prediction, and also classify the signals to understand in which region of the spectrum some particular users are appearing. And we use this information to improve the wireless transmission performance in a multi-user scenario also. So this is how we use this kind of spectrum knowledge in the group. So thank you. That's it. And thanks for your time.
Okay, so thank you very much, Sriraj. This is a very, very interesting, very modern topic you've been talking about. I I'm thinking of last year. You know, in last year's STRA, we already had this kind of topic, at least as a, well, from some speakers who contributed to that. There was Florian Brauchle with an implementation and applications of the spectral correlation density, and we had Alberto Dassati and Oscar Rodriguez Salona about deep learning inference in GNU Radio with ONNX as an import-export format for artificial intelligence applications, and well, we had these topics already. So we're seeing a big development here, and something I'm very happy about is that we have an entire block now. We have 4 talks altogether on the field of artificial intelligence plus radio signal analysis. So this is obviously a very interesting domain, a very interesting field of research. So, well, what I've been thinking about is, okay, you're trying to classify signals, you're trying to train, a neural network or whatever, but generally what you can do, or what you generally do, well, I have a background in computational linguistics, so this is the perspective where I see it from. So you have a gold standard, and you're training a system, but the system will only learn things that it's seen before a certain number of times. The interesting part is where a completely new thing comes in, a thing that the system has not seen before. This is one aspect. The other aspect is from the talk before with Adrian, and also other talks before, and OpenWebRX and the Kiwi SDR application, where you have kind of time difference of arrival location finding systems. This is actually also something interesting, and you know, in amateur radio, we have this special sports of fox hunting, you know, where you have transmitters in the landscape out there, distributed and out there somewhere, right? And I always figure out, hey, that could be interesting, automatically finding them. And okay, this obviously spoils the sport, but it's an intellectual challenge. Right. So there are many interesting things around this topic, and I would like to thank you very much for this contribution. Michael,
do we have some time for a question? Yeah, Siraj, what do you think? Maybe you have heard of the radio club or the German radio club project ENEMS, which is tries to identify the noise level on shortwave from 50 kilohertz up to 30 megahertz. And do you think that your algorithm can be trained to identify several different noise sources, which could be VDSL, power line, solar power optimizers, and so on?
Yeah, sure. Like you can definitely do that. So if you have training data for those kind of noise sources, we can train them in a supervised fashion also to detect them. Even if you don't have like labeled data set that says, okay, this noise source is a particular from some solar panels or something like that, what you can still do is like you can train it as an unsupervised anomaly detection problem and then try to localize these ones. So it's definitely doable, and as an anomaly detection problem you can do it for sure. Like and the code is kind of open source, so if you want to try it or if you need any help with that, I'll be glad to help also.
Okay, yeah, well, your system is now limited to use an RTL SDR and a Raspberry Pi, as I showed on the website. And well, it would be nice to have a deeper view on the shortwave spectrum, as this is very important for the further use of radio sports or amateur radio on shortwave, since we have a lot of influence by several noise sources, even the home electronic systems by power supplies and everything. Yeah. So thank you
Yep.
very much. Good idea, and I will have a look on it.
Yep. Thank you.
Also, big thanks from my side here. Interesting talk, and we'll continue with the similar topics since we have an entire block of these topics now. I'd like to welcome here Sriraj. We'll see you again in the panel then, so we can discuss those things later on.
Yeah, bye.
Okay, I'd like to welcome Stefan Scholl, Delta Charlie 9 Sierra Tango. Hello, Stefan.
Good afternoon.
Good afternoon.
Hello, Stefan.
So, good to have you here again. You've been a contributor to the SARA in the past also with very interesting topics like time difference of arrival. I think that was your first contribution years ago. And by the way, concerning statistics, we've been talking about statistics, right? Concerning about statistics, one of the most heavily requested contribution in general, looking to all our 100 videos. So that's something that interests many people out there. And you've come back also with a very interesting topic that matches perfectly here in this block. And the topic is classification of shortwave radio signals with deep learning. So Michael, I think that also agrees with your interest very well.
Yes,
the audience,
indeed.
Dear audience, for those of you who don't know Stefan, let me briefly present his biography to you. So Stefan holds a PhD in communication engineering and microelectronics, and he's currently working as a researcher at Fraunhofer in the domain of radar technologies. Well, Jean-Michel, Stefan is also an interesting contact for you. It's all about bringing people together, right? And well, radar electronics, and he's interested in signal processing and hardware for software-defined radios. Okay, as previously done, we are going to hand over to my video studio control colleagues. Please, video team, play the pre-recorded video.
Hello, everybody. My name is Stefan Scholl, and in this presentation, I will show how you can classify radio signals from the shortwave band with modern methods of deep learning. The talk is basically split up in 3 parts. The first part is about signal classification. Why do we use it, and what is it basically? The second part is dedicated to a brief introduction to neural networks and machine learning. And the third part is about an experimental system I have built that can classify shortwave signals into 18 different modes. So first of all, you can see a shortwave spectrum here. I've taken this from the well-known web SDR at the University of Twente, where you can view the whole spectrum from 0 to 30 degrees in one waterfall diagram. What you can see in this waterfall diagram is which frequencies are used. So where is somebody transmitting? What you cannot see is what the actual transmission mode is and how you can decode these signals that are there, how you need to set your demodulator or your decoder. I've copied out of the spectrogram a few signals, and you can now test yourself if you are able to determine the modes of the signal by just looking at the spectrogram. The signal on the left-hand side is very characteristic because it has some on-off keying pattern and is very narrow band. And this signal is a Morse code signal. So you can basically see the Morse code in the spectrogram. The second signal you can see here is very typical for AM broadcast signal. It has a very wide bandwidth, and the spectrogram is highly symmetric. The third one is already a little bit harder. So this is typical for an SSB audio transmission, especially here in the lower sideband. This signal here is a HF fax signal. You can see from a very strong signal here, which is not perfectly centered in the band. Now it gets really hard. Look at this signal. It's very narrow band, and you can't actually really determine what it is. It's PSK 31, but it could be anything else like a pure carrier or another transmission mode that has a very narrow bandwidth. This signal here is a digital signal. It's Olivia 4500. It's a 4 FSK signal. It's very hard to see. You really need to be an expert to figure out what this signal is. And that for this signal, you need to set the decoder to this mode. So you can figure out the mode by looking at the spectrogram, but it's sometimes quite hard and you need to have a lot of experience. So if you're an expert in that domain, it will be quite easy to determine a lot of modes. But if you're not so used to looking at spectrograms in the shortwave bands, it can be really hard to determine the modes. And what we want to do now is we want to see how we can automate this process of classification of modes. What is this good for? First of all, classification of modes is good for band observation. So we want to see what is going on the bands, not just which frequencies are occupied, but also what type of transmissions are there. This is especially interesting for example, for intruder detection, a problem we have very frequently in the amateur radio bands. And also for officials, it's important for law enforcement to see if everyone is transmitting in the band where he is allowed to. Another interesting application is about rare mode operations. In amateur radio, we often use the same modes like Morse code, SSB, RTTY, PSK, the weak signal modes from Joe Taylor. But there are a lot of other different and highly interesting digi modes from a technical point of view. For example, there's Olivia mode. I've mentioned this one before. It offers a live chat with very low SNR, like -10 to -15 dB SNR. And there are also other modes like MT63, which is a OFDM-like mode and is a very robust mode. And also Domino X, though it is not so fast, it's a very robust mode. The situation you encounter in practice is often like this. You see a strange signal on the bands, you might find it interesting, but since you don't know it, you just skip it. And so you cannot establish any communications with that mode. When you're interested in digi modes, I can also recommend this paper here. It's from Niels Schiffauer, DK8OK. You can download it. It's in German, but you can understand. Also, if you're not good at German, he shows different digi modes and analyzes the performance of this mode, which is very interesting. Automatic mode classification is also important for the professional domain. Here in cognitive, we have cognitive radio as an emerging technology. Cognitive radio means you have a kind of intelligent radio that adapts itself to the spectral environment. So there is not a fixed frequency and not a fixed baud rate and also not a fixed modulation and bandwidth, but the radio looks for free spectrum and for a spectrum where it is allowed to transmit and transmit its information there. And classification of modes is one requirement to enable this new technology. So mode classification, what it is about is you have a received signal, you have some kind of processing machine, and this machine outputs the transmission mode, which could be Morse, SSB, audio, Olivia. We have seen these modes already. And these outputs are called the classes, and this type of problem is a classification problem. The problem of mode classification is highly related to automatic modulation classification, where you input a signal, do some classification processing, and the output is a modulation type, like phase shift keying, frequency shift keying, and so on. However, determining only the modulation is not enough to decode and demodulate the mode, so it's not enough to read the transmitted messages. When you want to build a classification algorithm, you have basically two options nowadays. You have the classical way and you have the modern way of machine learning. The classical way means you try to find some characteristic properties or features of a signal, and you build an algorithm step by step that calculates these features. This is a very good approach for well understandable problems where you have a theory, for example, or where you have a deep understanding of these characteristic properties you require to distinguish between the classes. A more modern way is the machine learning approach. In a machine learning approach, you first collect masses of data, and then you train a complex mathematical model with that data. And this is something that is very good for problems where you cannot directly figure out characteristic properties. And this is applied, for example, in image processing with great success. It does not mean that machine learning is always the best way, but it seems that for some kind of problems, this new way of machine learning classifiers are highly superior. To make the difference clear between classical algorithm design and machine learning, let's assume a little task. You have to build a detector for AM broadcast signals. So an AM broadcast signal, the spectrum is depicted here. And the first thing you would do, you would find out what are the characteristic properties of these signals. What are properties that make an AM broadcast signal different from other signals? And by looking at the spectrum and by having some experience, you could figure out maybe 3 properties. One is the bandwidth should be larger than 3 kilohertz. This spectrum is symmetric, so upper and lower sideband are symmetric. And there is always a large peak at the center frequency. These 3 properties I've chosen some kind of arbitrarily. You could probably choose anything else, and it's probably not the best way, but it is good to show the difference between the algorithm approaches. And once you have identified these 3 properties, we can build an algorithm that calculates these properties. So in this case, it could be you input IQ samples, you do some FFT to come up with a spectrum, because all these properties are defined in the spectral domain. And then you can take an algorithm, some algorithm that calculates symmetry, some algorithm that calculates where the center peak is located, and some algorithm that calculates the bandwidth. And you take these 3 measures and you combine that into a logic, and you can determine if the signal is an AM broadcast signal or not. The advantage of this approach is that this algorithm can be fully understood by the designer, which sounds somehow natural, but we will see in a minute that this is not the case with machine learning. And you can easily debug this kind of classifying algorithm. Let's assume you have built this machine. You input an AM broadcast signal, but the output tells you it's not an AM broadcast signal, so it's a wrong decision. You can then go back and check where the error in this processing chain has happened. Perhaps you could go back, look for the measure of symmetry, and maybe you see, oh, it's not symmetric. So you can even go a step back further and have a look at the spectrum, and maybe you can see in the spectrum, oh, it's not symmetric. So there's a kind of way to improve your algorithm by kind of debugging. But there are also some disadvantages. are these three features really good, or are there features which are even better? Yeah, this highly depends on the experience of the algorithm designer. And for some problems, it's even very, very hard to find characteristic properties. Let's think of a task in image processing where you have to distinguish between cats and dogs. Look at these 6 creatures. It's very hard to derive characteristic properties for cats that make them different from dogs. So for this kind of application, classical algorithm design is very hard, if not impossible. The machine learning approach is an entirely different approach. First, you collect masses of data. You collect a lot of AM broadcasting signals, and you collect a lot of signals that are not AM broadcasting signals. Then you take a mathematical model with many free parameters. You do some kind of training, and in the end, you come up with a model that has fixed parameters, and that defines basically formal calculations to detect an AM signal. What is the advantage here? Its features can be very good since they have been obtained automatically by looking at the data in the training process, and the designer does not require any expert knowledge. However, it is often unclear how the model designs because there is no well-defined meaning of all these calculations in a mathematical model. And therefore, it's also hard to optimize analytically. A very commonly used model in machine learning is a neural network. A neural network is basically a model of the human brain, a very simple model. It consists of neurons, these circles here, that are connected with each other. And on the left, you input some data. This could be a signal or a spectrum of a signal or pixels from an image. And this information is processed from left to right. And on the right-hand side, you have these output nodes which correspond to the classes. Every neuron has a very simple behavior. It consists of several inputs. In this case, it's 2, x1 and x2. And each input is weighted by a weight, w1, and for the second input, it's w2. And you add up a bias value, and after that, you take some operation which is called ReLU. ReLU means rectifier linear unit, and basically it means that you force negative values to 0. And every neuron has one output that is calculated by this simple equation. You could also have a neuron with 3 inputs or more inputs. Then you again weight every input by a value, and you add again a bias and take the ReLU operation to form a neuron that is a little bit more complex. To make the thing more powerful, you can now combine several neurons to form a neural network. Again, we have a neuron here with 2 inputs. We have a neuron here, a second one with 2 inputs. And we have seen on the slide before, you can calculate a neuron and come up with this kind of formula. So it always consists of weighting, adding a bias, and taking the ReLU operation. And the same thing you can do here, but the weights are different and the bias is different too. And you can also go a step further and build some kind of hierarchical structure where you feed the outputs as an input to a third neuron. And again, you weight the inputs, you add a bias, you take the ReLU operation to form the output. And here we have a very simple network with only 3 neurons. And you can see it's already a quite complex formula. So a neural network is nothing else than like a complex function that has many free parameters that can be fixed. Weights and biases can be fixed later during the training process. An even more complex neural network. You can see that now the hierarchy is larger. We have arranged the neurons in different layers, 1 layer, 2 layer, 3 layers. And this network already has 41 weights, 10 biases, and 10 times a real operation. So the output here is really a very complex function now. And you can add also a second output neuron. And there is also a function defined for the second output. And every output neuron corresponds to one class. And the neuron here has like the formal calculation to detect the class 1, and the neuron here it contains the formal calculation to detect the class 2. So there are different types of layers in a neural network. What we have seen so far is a dense layer, where every node is connected with every other node. It's called a fully connected layer, and it contains a lot of weights, and it's quite complex to train. So researchers have come up with some more structured layers. One very commonly used layer is the convolutional layer. The convolutional layer has some very specific structure. A neuron is only connected to very few preceding neurons. And there is also some kind of structure. When you have some knowledge on signal processing, this kind of structure may be familiar to you because it's a convolutional structure. And in radio signal processing, you often talk about filters. And what you do is in a convolutional layer, you often put several filters in parallel to enhance the power of this layer. And there's also a third one, a pooling layer. Pooling layer basically means you take the maximum out of 2 input layers. And the purpose of the pooling layer is to reduce the number of neurons in a layer, to reduce the neural network in order to make it not too complex. A typical convolutional neural network is used in praxis. It is based on an input layer, and then we have some convolutional layer with several filters. And after that, you have a pooling layer. Yeah, you could also have like 2 convolutional layers and a pooling layer, or even more, but it's always the structure of having convolutional layers and then pooling. And then you repeat that again, convolutional pooling. And you could also take like a third step of convolutional pooling. This is a very typical approach when designing modern neural networks. And in the end, you have some kind of dense layer, densely connected layer, which are connected to the output layers. To the output layer where each neuron corresponds to one class. The term of deep learning refers to neural networks that have many layers, like tens or hundreds of layers, because deep learning neural networks are very powerful, are hard to train, but are very powerful. I want to give you an example of a neural network that is very famous. It's the AlexNet. AlexNet is a network that can do image classification. So you can give it an image, and he will determine what can be seen on that image. And it is able to distinguish between 1,000 classes. Yeah? For example, you have like a mite here, a container ship, motor scooter, leopard, and so on. There are 1,000 different classes. The input layer of this network has 150,000 neurons. It has 8 layers in total and 600,000 neurons in total. And here you can see the structure of this network. It's some kind of convolutional network. And in total, it has 60 million parameters, so 60 million weights and biases. So this kind of processing that we have here is very, very complex and though also very, very powerful. The question is now, how do we determine all these weights and biases? And that is done during training. A neural network can basically operate in two modes. One is the training mode and the other one is like the prediction mode, or where we use the neural network to make predictions. In the training mode, you feed in data, you determine the weights and biases. This is a very complex process. This is done usually in the design phase, and you can also, you have to do it once. So you can put a lot of effort in training neural networks in terms of like high performance computers and in terms of calculating this training for a very long time. And once it is trained, you can deploy it. Weights and biases are fixed, and you can basically use the network by just inputting unknown data and outputting, and it outputs the classification result. And calculating the prediction of a neural network is a quite simple task. We have seen before that the neural network is basically having additions and some multiplications, and that's it. So not many complex operations. And it's also very good for parallelization on a GPU or on a computer chip. How does training work? First of all, we need data. So a data set consists of the single data, which could be a signal, a radio signal in our case. And you need to have the data label. The data label is in our case like the true class, which could be a Morse code or any other radio mode. And these labels are usually very hard to obtain because you need a lot of data, and like labeling this data is usually done by hand or by using some kind of synthetic generation of data. When training a neural network, you first initialize the weights and biases randomly. Then you take data, you calculate the output of the neural network, which is basically of very low quality because all the weights and biases are just random values. And you compare that output with a true data label. And obviously in the first place, it's very probable that the output of the neural network is not the correct class. So what you do then is you do some kind of training step. That means you modify all weights and biases such that the network output gets better. So usually you use some kind of gradient descent algorithm for that. It's called backpropagation. And once you have done this, the weight gets a little, the neural network has a little bit better weights and biases. And you do that again with the next data, this process. And you do that, you repeat that process for all data in the data set. And if you have done this, it's called an epoch. And usually during training, you don't do just one epoch, but you have many, many epochs, like 10 epochs, 100 epochs, or even more. And over the time, the network trains to get better, and in the end, you come up with a neural network that is able to classify the data very well. Okay, so this is how you can build a neural network, how you can train a neural network. And in the next step, we will check how we can build a classifying system that detects 18 modes that are commonly used on the shortwave bands, also under noisy conditions. And the question is, can a neural network learn shortwave radio signals? First of all, we have to talk about the data set and about the modes that the classifier can distinguish. The 18 different modes are depicted here. It's, for example, Morse code, PSK 31, PSK 63, QPSK 31. Some RTTY modes, which have Here, these two modes have a very high similarity. So it's both FSK, 170 Hertz of shift, and the baud rate differs only by 5 baud. We have some modes from the Olivia type, Domino X, MT63, Navtex, USB audio, LSB audio, AM broadcast signals, and HF fax. So there are also some analog modes. And as you can see in this column, the modes cover widely different modulation types and also different baud rates. The question is how to obtain the training data, because you really need a lot of data for training. My approach here was to generate the data synthetically. Synthetically means I take software like FLDigi to generate the modes for the digital transmissions, and for analog transmissions I take speech and music, and I use some kind of analog modulator, AM and SSB, to generate the baseband signals. Then I add some kind of noise from an AWGN channel, such that the resulting signals have an SNR between -10 to 25 dB. Next, I add a Watterson model. I will talk about this in 1 minute. And finally, I add some random frequency and phase offset. So the frequency offset is here between -250 to +250 Hertz to account for a small mismatch in tuning. The Watterson model is a special model that simulates the properties of the ionospheric HF propagation. So basically, this is a model that introduces fading. And it does so by modeling the transmission as a multipath propagation, and by adding random Doppler spectra. So you have an input here, some delay line, and you have some signal components at different delay times, and these are altered by a random Doppler spectrum. The CCIR 520 standard provides practical values to parameterize the Watterson model, and there are like these 5 fading channels defined, like good, poor, pure, moderate, flutter, and Doppler, that are used in my training set generation. The output of the training set are signals that have 2048 IQ samples. That corresponds to a recording time of around 300 milliseconds. The bandwidth is up to 3 kilohertz. In total, I have generated 120,000 data signals for training and 30,000 additional for testing the neural network. The data set I've generated is available on my website, canaradio-sdr.de. This is what the data looks like in the data set. For example, here are some Morse code signals with high SNR, medium SNR, low SNR. The PSK signals are shown here, and some exemplary FSK signals can be seen here. So you can see the IQ signals, you can see the influence of SNR, and there's also, you can also see the influence of frequency offsets, which is quite high here and a little bit lower here. So we have generated a variety of different signals that can be used now for training. The neural networks I've built, there are 3 neural networks that can be used for the signal classification. They all have around 2.4 million parameters. The first one is a classical convolutional neural net with 8 layers. And it consists of convolutional layers followed by pooling layers, the structure we've seen before several times. And in the end, we have some dense layers. The all convolutional net has only convolutional layers and no pooling. It has here 13 layers. The deep CNN has here 17 layers, and it's composed of convolutional layers, always 2 convolutional layers and 1 pooling layer. And again, the same structure repeating again and again. The residual net is a very powerful net. It has 41 layers, and it's really hard to train such a large neural network. So researchers have come up with this kind of technique, which is called residual connections, that make training possible for these kind of deep layers. And you can see the residual stack that has been introduced by O'Shea, which can be used for classifying signals. And what is characteristic in this structure is that you have shortcuts here that like circumvent certain layers. And that is a kind of trick to make training more robust. This is how the system was trained. On the x-axis, you can see the number of epochs. So I have trained for 30 epochs. And you can see that how the accuracy changes, the accuracy of the classification changes over training. You can already see after 1 epoch. So 1 epoch means every data has been fed into the training algorithm once, that the accuracy is at 70%, which is very good. Because if you choose randomly among the 18 modes, you would come up with 5.6% of accuracy. So it's already after 1 epoch, the network has learned a lot to distinguish between these 18 modes. And then after 30 epochs, you come up with accuracy, for example, here of 94%, which is pretty good value. The training is done with a TensorFlow software using an atom optimizer, and the training time here is around 1 to 5 hours on a usual desktop PC, depending on the net you want to train. Here are the results of the accuracy over SNR. So SNR, you can see here on the x-axis. On the y-axis, we have again accuracy. An accuracy of 1 means it can perfectly classify every signal. And the first thing we see is that classification performance is dependent on SNR. So for very low SNR, the network is not working so well as it is with high SNR values. But for high SNR values, you can see that an accuracy of 98% can be obtained. And this can be obtained by the ResNet, by the residual net, the one with a large number of layers, 41, and the deep net. The other networks with 8 and 11 layers, they are a little bit inferior. But you can also see that for this neural network, it's possible to go beyond an accuracy of 95% for high SNR values. So the learning of this synthetic data was very successful. Okay, I've shown how this classification system can be built for 18 different modes. With recent technology, we have in deep learning. And for synthetic data, it was possible to achieve a very high accuracy. So this is a very promising result. Nevertheless, the data was synthetically, and it will be a task of the future to analyze the performance of this classification system for real-world data. And what is also interesting is to include more modes. Now I have considered 18 modes, but in reality, on the shortwave bands, it is believed that there are hundreds of different modes. So this concludes my talk, and I thank you very much for your interest.
Stefan, thank you very much. This was a very interesting talk again. in fact, we have a block of artificial intelligence talks here, and personally, what I find most interesting is that you've presented the fundamentals of artificial intelligence very, very understandably, right? So that even if you don't have a background in artificial intelligence or in statistics, you see those layers, you see how they interact. But nevertheless, I have a question. Maybe I've missed it because I've been researching in the background a little. What is the minimal data item you're working with? Because that's kind of difficult. I mean, in computational linguistics, it's obviously a word or a trigram or n-gram, so that you're putting words together. Because if you're talking about statistical analysis in terms of language, you always have pieces of a language in close neighborhood. So, but what is the minimal data item which you can use in order to classify a signal? Because a signal is a stream, like in language, but you have to chop it into pieces. What do you do there?
Yeah, that's exactly what I do. I chop it into pieces. So it's always 2048 samples, IQ samples, so complex samples with a sampling rate of 6 kilohertz. So I'm just looking at the signal portion that has a duration of approximately 1/3 of a second. So this is very little. But in fact, the results show that this is enough to distinguish these signals. Of course, if you have a signal that varies very slowly, like the weak signal modes, then looking only at like 0.3 of a second is not enough, and you should have a longer look on the signals, maybe over some seconds.
Okay, very interesting. Thank you. Well, we have a couple of questions here in the chat, but we're behind of time. Your talk was longer, and we didn't modify the schedule so much, but we also have a shorter talk now, so it matches together again. I'd like to keep the questions for the panel later. So we'll see you again, Stefan. Thank you very much again. And I'd like to call in our next speaker, who is Bart Sommers, Papa Echo 1 Romeo India Kilo. Hello, Bart.
Hi, good afternoon.
Hello, good afternoon. Thanks for coming in. Dear audience, Bart is going to speak on the following topic: frequency band occupancy measurements with statistical analysis. Once again, it's a topic on statistics. And for those of you who don't know Bart, I'm going to present Bart to you. So he got his ham radio license in 1996. A few years ago, when cheap SDR receivers came available on the market, he switched from HF to learning SDR and GNU Radio, and he loves to combine Raspberry Pis, SDRs, antennas, and programming in Python. And currently he's taking his MSc, his master degree in computer science at the University College of Dublin. So, dear audience, as we do that, usually we've pre-recorded Bart's talk, and I'm handing over control to our video team. Please, video team, go ahead with Bart's presentation.
Hello, my name is Bart Sommers, Papa Echo 1 Romeo India Kilo, and I would like to introduce you to my current project. It's frequency band occupancy measurements with statistical analysis. And of course, I'll use GNU Radio for that and Python. Just a little background on my presentation. Last year on the Software Defined Radio Academy in 2020, I gave a presentation on SpecMon, spectrum monitoring, and I was using it to monitor spectrum over a long time. It allows us to determine patterns in spectrum usage. The frequency piece I was monitoring over there was the 2-meter ham band, and especially the repeater downlink band. And that's an effective piece of 200 kilohertz of bandwidth. But that's actually just 10% of the entire ham radio band. And this is one of the presentations, one of the slides from the presentations from last year. And as you can see, over the 24 hours in the day. This was May 5th, 2020. You see the usage over here, and it's just a few percent or just a single percent of usage, and it spikes here somewhere around noon. There was probably a meetup over there. The software I used had some limitations though. It uses integrations of samples to detect increasements of power and an integration time of a single second. This leads us to the problem that short bursts are not visible or they're just displayed as a single second transmission. And the scaling of bandwidth is difficult. If small power increasements will be difficult to see if you increase the bandwidth you are monitoring with this setup. The time resolution. 1 second time resolution is quite a big time frame. It's not for analog radio though. If you push your push to talk button and start transmitting out your NBFM transmission, of course you will be speaking for more than a second. But if you take AIS signals from ships, for example, one transmission is 26 milliseconds. And if you take a DMR or TDMA burst, a single burst is 27 milliseconds. And you want to capture those frames and not get them together in a single second. So we need a smaller time frame. So we need less integration time. The measured values becomes smaller, of course, but signals are still visible. And we can remove the running average in there. So I start doing some tests on small bursts. AIS signals, they do trigger the threshold. And I got more short signals visible in my measurements. Probably more spikes. Radio frequency interference can be a problem, but it's hard to determine without decoding. So the threshold becomes more and more important. The first experiment I did after this was to see if we can detect lightning. Lightning just increases the noise level or the power in a broad spectrum, so we might be able to see these changes. We need a piece of spectrum without users for this, of course. And in the Netherlands, in the EU, we've got some spectrum allocated for radio astronomy. Or in this case, I used a piece of our 10-meter ham band. And this 100 kilohertz I took was the part between the repeater input and output on the band. The measurement setup I used was my Lime SDR Mini on the frequency in the 10-meter band, and I just decimated to get 100 kilo samples per second, so that's 100 kilohertz. A relatively low gain, and I used my disc cone antenna for this. Lightning, well, you can hear it, and you can hear thunderstorms, but you never know how far away they are. So I compared my results with blitzordnung.de, and I measured from August 8th until August 31st in 2020. Lightnings can be detected, of course, over a long distance. The lightning storms are pretty high up in the sky, so your line of sight is pretty long. Percentage of usage in this case, of course, is not useful, but the amount of discharges is quite interesting. The minimum time frame of the new software version was 100 milliseconds, but if we take a look at August 29th last year, you can see there were some lightnings, and in the morning there came some more, and in the afternoon it became even more, and late in the evening the day ended with quite a lot of thunderstorms. Within this last hour I measured almost 700 increasements of power, probably discharges. One day after it was August 30. You can see in the afternoon some more, and in the evening even more, but that's 2,600 discharges I measured over there. There were some thunderstorms close by, and yeah, there was quite a lot of lightning over here in the city. But still I couldn't compare them. So what I did was I took a screenshot from Blitzordnung. I'm measuring per hour, and they do snapshots for 10 minutes. So that's a little bit difficult to compare, but 1925 UTC, so that's 2125 local time over here, and they still already have 11,400 discharges. I monitored this for several days, and well, the graphs, they really line up. So yeah, it's possible to detect lightnings. There was another problem with the bandwidth which I would like to solve, and that was the problem of scaling the bandwidth. So how do we solve this? Well, let's take FFTs and do a peak find in the band of interest. You have to choose your FFT bins and your FFT size wisely. Narrow band signals require smaller FFTs. I compare them with the International Telecommunication Union, and they advise you to use 6.25 kilohertz widths of bins for your FFT sizes. I think they're pretty big. If you take very small band signals like CW or FT8, they probably got drowned within the wide 6.25 kilohertz. So better you could take something like 500 hertz or a kilohertz and start monitoring with that. I use the FFT block in GNU Radio, and I want to FFT just every sample. I don't want to drop anything. I use a complex to magnitude squared for the power indication. I integrate some vectors. Yeah, this limits my time frame, but after normalizing, I can really see some interesting results in the values. And then I do a peak find. When we want to find a peak, we do need to have something like a threshold, because there always will be peaks and very small peaks, as it's just noise over there. So we need to have some threshold to, well, trigger it is it comes above this this baseline. And if it's above my threshold and under my threshold, just exactly like last year, we just print out the line with the timestamps, but now with a smaller time frame than a single second. Peak find, though, works great when the spectrum is really flat. Signals above the baseline will trigger the threshold, but the spectrum isn't flat. It's curved at the edges, do the FFTs, or do your SDR, and you might have some DC peak remainders in the middle of your spectrum. And this is a sample snapshot I took. As you can see, it's pretty low down here, and we've got a DC peak remainder over here. Yeah, there is a DC peak filter, but in this case it drops down, but it also can have a little peak up here, which would limit your threshold. And see this bump over here. I can't put a threshold lower than this, as it would always trigger the threshold. So how do we solve this? Well, I was thinking, and I found the log 10 block into GNU Radio. It says n times log 10. So yeah, we want to have n equals 10 for a dB-like scale. And then we've got the magic k over here. And if you fill in the k, you just lift the spectrum. And you lift the spectrum everywhere for the same ray. As you can see, it's just exactly the same line, but it's lifted a little bit. So this made me think, what if every item in the vector could have its own k or its own constant? Can we flatten out the vector? And it appears, yes, we can. Not with a log 10 block, but with adding a vector. So I call this a calibration vector and use this calibration vector as k or the constant. So we need to calculate this calibration vector for your setup. And with a constant value, for example, 0, and then we have to measure some values. And the measured values we take for this baseline, this calibration, are created with a dummy load. So your entire setup, don't connect an antenna, connect a dummy load, record something, and from the recorded values, create your baseline, your calibration vector. And guess what happens? My spectrum is flat. The DC peak is away, and this bump is away over here. But as it's just a constant adding, if we've got a little increasement over here, the increasement over here will be exactly the same. So now I do have a very flat spectrum, and this little green line over here is my baseline, which is a very flat baseline. And if we zoom in a little bit, you can see, well, it's just wobbling away with some peaks, but this is just noise. Well, we do have a flat baseline. We can use a flat threshold. That's awesome. And my next step would be measure the sensitivity. And I took two measurements, one with my RTL SDR V3 and with my RSpy R2. So I fired up my 1971 Marconi signal generator. It's made with tubes, so it took some time to heat up. but with some friendly amateur who calibrated this at 0 dBm output, I can use this as a reference. Reference in a 2 meter ham band. Then we've got a 0 dBm output. Into the attenuator, and I can switch and switch until I've got my required signal strength. The antique Marconi, I really love the machine, but it's made with tubes, so it takes an hour or two to stabilize. After that, you're pretty sure you can keep your coffee warm on top of the signal generator, and then start saving vectors with the dummy load, create a calibration vector, and use that as a calibration vector with the GUI to start tuning and see what's happening. My RTL SDR, well, this is a peak of minus 95 dBm. As you can see over here, it's a value approximately 20. Well, no things about it, just 20, which I measure over here. And this is just the noise. As you can see, we've got a threshold over here. It's way above the threshold. Minus 105 dBm. This is interesting. It's approximately 11. That's also 10 values lower with 10 dBm decreasement of signal. And then at minus 115 dBm, you see we've got a very small peak over here. And this is the threshold. I can reliably detect this, but if I lower the threshold, the noise peaks will start generating false positives. So this is neat. My RSPI R2, minus 114 dBm. It's also approximately 20, well, it's 23 over here. Minus 130 dBm, and it's still a nice peak. We can clearly detect it on this one. Minus 134 dBm, and this is almost the limit to detect. But as you can see, it's, well, 4 over here, and we had 24 over here with 20 dBm more. So that's also neat that we've got 20 decrease with 20 dBm decrease of signal strength. So with the RTL SDR in this software version, I can reliably detect signals from minus 115 dBm. I managed to get minus 125 dBm with a higher gain, but with a higher gain in the RTL SDR v3, you can get some problems when signals are increasing on the front end. And with the RSPI R2, minus 134 dBm is pretty good to detect. With a gain of 20, maybe we can get some more gain or and have some better sensitivity, but haven't tried it out yet. And both SDRs increase output with 10 when the input increases with 10 dBm. So now it's time to start spectrum monitoring with a flat baseline and a known sensitivity. We use the same method, SpecMon from 2020, although with new software version, above and under the threshold. There's a little change in the software. This is the low average. So this is the average low value between two measurements. So if you look at these values, you might be able to see noise levels changing, but I haven't made graphs out of that yet. The next images all were made with my RTL SDR v3 on a Diamond V2000, and I used a triplexer because it has a nice band pass filter. Besides this band pass filter, I used a broadcast FM filter because within 100 meters from my house, there's a broadcast FM transmitter, which is really messing up some signals over here. 2 megasamples and a gain of 20. So on a center frequency of 145 megahertz, I take the entire 2 meter ham band. And then I start monitoring, and I got some graphs. 100% usage in the middle of the night and in the evening. What was happening over there? But some pretty normal usage over here and some patterns. This is the percentage of usage, and this is the average opening time. And as you can see, the average opening time is 3600 seconds, so that's exactly 1 hour. What's happening over here for 5 hours continuously at transmission? That's weird. Another day, Friday, May 5th, we got almost the same pattern over here, and still, well, continuously transmissions where something was open or transmitting over here. So I really needed to figure out what was happening over there. And then lucky, Sunday, May the 9th, there was no RFI this day. And you can see pretty normal usage over here. Interesting to notice that this peak over here, in the end of the morning and the beginning of the afternoon, is almost the same all days. And then in the evening, usage starts increasing. And over here, there was some more increasement. If we take a look at the average opening time, it's all low. These are just repeaters sending out their call signs, some beacons in the band, and some all small transmissions, seconds, 30 seconds. But over here, we've got 1700 seconds openings time. And yeah, there was a meetup on a local repeater. So the local repeater was transmitting that time. There were weird peaks in the measurements. What happened over there? Well, lucky I saved the vectors. So I didn't need to record all raw IQ recordings, but I can just save the vectors, which I use to my Specmon block into GNU Radio. And I can replay these vectors. And that's approximately 75 megabytes per hour. So still, if you keep this running on your Raspberry Pi, on the SD card, you can save several days of data and afterwards see what was happening over there. This is pretty much a normal view of the band, and these peaks over here, that's RFI. These peaks are always there. They limit my threshold. This green line over here is the threshold, and all the other signals are real signals in the band. One thing which is pretty strange, 145.150 kilohertz, sometimes there's for a long time a signal. And that's not something which is mixed into my SDR, because I heard this signal also with my ham radio transceivers. So there is something in my neighborhood sometimes transmitting on this signal. So some RFI. But this was what was happening in the nights. And every 130 kilohertz, there was a huge peak. And this is the entire 2-meter ham band. And the signal is there, and it's continuously there, and is there for hours and hours and hours. I haven't figured out what it is, but it's coming back almost every night. I was lucky I received one day without these signals. So I have to figure out what this actually is. So with the conclusions of this software, we are capable of monitoring an entire band, and we gained some high sensitivity in there. We've got a reliable threshold over the entire band because we can flatten the spectrum and have a flat threshold. It does trigger on narrowband signals, so FTA triggers, a CW signal triggers, even when it's a weak signal. Long-term monitoring is possible. I tried that to detect patterns, and the interesting, well, not so lucky patterns I detect were RFI patterns, which I really need to figure out. And still, it runs on a Raspberry Pi. You might have mentioned I'm still running on GNU Radio 3.7. Debian Bullseye will be released very soon, and then we switch to 3.8. And again, we need to lower the time frame even more to get some very small bursts. Well, I would like to thank you for watching my presentation. You can find the software on my GitHub page, which I mentioned over here. And if you have some additional questions, please send me an email. Thank you.
So Bart, thanks a lot for this contribution. Very interesting, very insightful. And yeah, Michael, Michael's pictures looks like if it's frozen. But Michael commented here in the chat. He said that 130 kilohertz could be a power supply for LEDs during the evening in the neighborhood somewhere. So this could be the cause of your interference there.
Yeah.
Yeah. Well, that happens from time to time. Also around my sites here. Well, bad luck. By the way, particularly what I've seen and my Radio Shack, my radio site over Christmas time. I'm seeing big interferences over Christmas time because many people have their Christmas lightings out there, and they are terrible for the band. It's really pollution, high frequency pollution out there. That's really bad. Well, and I'm always glad when Christmas is over and when those light bands go off, when people mount them off again, so that there is some more silence on the bands and the noise floor goes down. Well, okay, very interesting indeed. A nice talk about statistics again, and yeah, I would have some more questions, but I'm going to save those questions for the panel, particularly on the well, so that you can think about an answer already by now. I'm going to think about the size of a corpus because, well, as I come from corpus linguistics, from computational linguistics, in corpus linguistics, there has been a big discussion about the ideal size of a corpus. How big should a corpus be so that you're getting best results? Is it linearly going better and better, or is it approaching to a ceiling where you won't get many more new insights? So can you limit the generation of a reference corpus of signals, and can you say, okay, the way it is, it's good, it's okay, or can it always be a little bigger, a little more data, and you're making the systems better the more reference data you have? So you can think about that over the next talk. Well, here in the chain we have another talk. Marcus Leach, who is a radio astronomer from Canada. Yes, okay. It's a standstill picture, and Studio Control says that Marcus has been here in connected to us, but obviously there are some network problems right now. It doesn't matter. The audience, you see how Marcus looks like with a standstill picture, and I'm going to present Marcus to you. So Marcus has been involved in high technology development since 1979 and has had an interest in radio astronomy since high school. And he worked in various roles at Nortel for nearly 20 years and was involved in the Internet Engineering Task Force for 14 years, the IETF, having held roles as both Working Group Chair and Area Director for the Security Area. And he began applying SDR technologies in radio astronomy in 2004 and has been a user and contributor to GNU Radio since 2005. In 2016, Marcus created the Canadian Centre for Experimental Radio Astronomy to provide practical tools and techniques for small-scale radio astronomy programs in universities, colleges, and secondary schools. And CCERA has an active and diverse observing program where he's engaged in. And the topic of his talk will be about mapping the sky at 21 centimeters. And here, this talk is about GNU Radio in radio astronomy. So I'm handing over the microphone as in control over to my colleagues in over there. Studio Control, please play our pre-recorded talk.
Good afternoon. My name is Marcus Leach. I'm the current president of the Canadian Centre for Experimental Radio Astronomy in Eastern Ontario in Canada. Today I'm going to talk about a project we've been working on with Carleton University to run a dual polarization spectrometer for the 21 centimeter band. And while Carleton uses the data to teach undergraduate students about radio astronomy to compute the galactic rotation curve, we decided that we'd take the same data that we provide to Carleton and produce a heat map of the sky at 21 centimeters. So I'm going to go over all of that in this talk. So a little bit about me. I've been involved in high tech since around 1979. I've held various roles in IT, software development, technical standards, that sort of thing. I was a working group chair in the IETF for a few different working groups. I was an area director in the IETF for 4 years in the security area and assisted with the development of standards like IPsec and TLS and all of those things, helped shepherd them through the standards process. I hold a bunch of patents in cryptography and network security, mostly through my role at Nortel, but also through a couple of other companies. I got involved in amateur radio astronomy in 1986 on a project to build a 21 centimeter interferometer just outside of Ottawa. And I've been involved in amateur radio astronomy on and off since then. Whenever an opportunity presented itself, I would get involved. A ham radio operator since 1986, and I've been involved in GNU Radio since around 2005, both as a contributor and a user of GNU Radio in my radio astronomy work. I started the Canadian Centre for Experimental Radio Astronomy in 2016, and I've been mostly semi-retired since 2017, mostly focusing on CCERA and doing a little bit of consulting work on the side. So what about software-defined radio and radio astronomy? It has been a long road to acceptance of the technology in both professional and amateur communities, which surprised me. The first paper in the field was one that I wrote back in 2004, New Directions in Amateur SETI Receiver Design. But for about a decade, I was really the only person using SDR techniques in radio astronomy. Professionals weren't interested because the receiver bandwidths were too narrow, and they already had their own custom design hardware to do some of this stuff. And the amateur community at the time in amateur radio astronomy was mostly what I would have to describe as old school people who weren't that comfortable with computers and modern technology. So it took quite a while, but when the RTL SDR showed up, the technology became really cheap. So a lot of people thought, well, why not, try this out in radio astronomy? And so, yeah, about starting around 2014 or so, more people got involved in using the SDR techniques in amateur radio astronomy, and it's been really great since then. So there's been a lot of software packages out there since then. Virgo, the West Virginia University Radio Astronomy Lab has done a lot of work with GNU Radio and small-scale radio astronomy, and of course so has CCERA, and that's basically our mandate, if you will, is to work on small-scale radio astronomy techniques, publish our software, talk about our hardware designs, all of that kind of stuff. The very early versions of GNU Radio, like prior to 3.7, included some in-tree radio astronomy applications, which I contributed to early GNU Radio, but we pulled it out partially because some of the dependencies were unpleasant, but also because it was more of an application than a core functionality of GNU Radio. So it migrated out from there. So yeah, I started CCERA in 2016 for small-scale research and providing observing to support to post-secondary education. We have a relationship with Carleton University, as I mentioned, in support of undergraduate astrophysics. We were located in a small town called Smiths Falls from 2016 to 2021, but we recently have been relocating to a much smaller town about 15 kilometers away from Smiths Falls. So the spectrometer, this is the instrument that basically we describe as our bread and butter instrument. It provides ongoing data to our academic partners, and is used to produce sky maps and compute the rotation curve of our galaxy. The GNU radio component actually runs on a little Odroid XU4 with an AirSpy R2 as the radio hardware. We support dual polarization, as I mentioned, so there's basically 2 Odroids and 2 AirSpy units. And the Odroid sends integrated spectra via TCP at about 10 hertz to a PC, which further processes and logs the data and so on. So the goal for this work was to produce a 21 centimeter brightness map. So a brightness map ignores the individual spectral components and considers them together all as one brightness level, if you will. And we cover astronomical declinations from minus 35 to plus 75. So it's 110-degree coverage of the sky, which is fairly respectable given our location in the northern hemisphere, actually the northern part of the northern hemisphere. And the Doppler range we cover in the brightness map is from minus 160 kilometers per second to plus 160 kilometers per second. And as I mentioned before, we use ongoing Carleton University spectral data to calculate the brightness over the sky and produce a lovely map. And the other reason, of course, is that people relate more to pretty pictures than they do to other types of radio astronomy data. So it's nice to have a data product lying around that's an image, although a very coarse one, of course, given our spatial resolution, that you can show to people and say, this is the kind of thing you can do with radio astronomy. So there's a picture of our equipment. Of course, these pictures are now obsolete since we've moved from that site, but we were using a 1.6 meter dish with 2 LNA modules, and then that would feed over about 60 meters, 60, 70 meters of cable to the receivers that were in our receiver room. And you can see that there. There's 2 AirSpy R2s and 2 Odroid XU4s coming from the antenna. The antenna has a linear actuator on it, and the software moves it every 25 hours to a new declination. And it just keeps doing that all year long, just slowly moving up and down every 25 hours and recording what it sees. And then that data is collated, sent off to Carleton on a daily basis. And then we also use it for our sky map. So this is just a quick picture of our new site near a little town called Rideau Ferry. You can see that there's no buildings there, and it's on the ground, but it's actually a fairly nice facility in the science sense because it's further away from any large towns. There's 38 acres, whatever that works out to in hectares. It's like something like 15 hectares. And it's mostly barren and rocky, so there aren't very many trees to get in the way. And so it allows us to do a bigger variety of experiments without having to worry much about whether our landlord would be supportive of our activities and so on. So this picture shows the new mount for the 21 centimeter spectrometer. It's still in progress. We are hampered by weather here, and also the fact that the province I'm in is currently in lockdown, so it's much harder to get work done. So this will be the new mount for the new 21 centimeter spectrometer. We're upgrading to a 2.5 meter dish, keeping the same feed and all the same back-end electronics and so on. And the equipment, once it's all in place, will be housed in a trailer. Rather than a building, although in the future we may put in a permanent building depending on what the site owner allows us to do. So that's a flow graph. It's probably a bit hard to see, and it actually looks much more complicated than it really is because it supports 2 receivers. The reason for that is that that allows you to also do what's called differential radiometry, where you use one channel either as a, you put a terminator on it or a cold noise source, or have a secondary antenna that points at a cold spot on the sky, and then the other channel is used to compute differences. But this flow graph basically is just two copies of more or less the same thing. It computes a spectra, and it also computes the total power in each channel. So just a complex to mag squared, and integrates it with IIR filters, and then it just sends it to TCP sync after it interleaves the data, so it can go over a single stream. It's actually two streams. The spectra go over one stream, and the other data products, if you will, go over the other. So it's the total power for both channel, and the differences go over one channel, and the spectrum goes over the other. And this runs on a little Odroid, and we have just a pretty generic rack-mounted PC that collects this data, as well as data from a lot of other experiments that we do. So we've got sort of a centralized location for the data to live in, then get distributed to our partners. And the actual radio receivers are typically on their own little dedicated Odroid or similar single board computer. So what do these spectra look like? That's typical at the site that we're at in Smiths Falls. There's you can see that there's a spur there, a fairly strong spur in the data, and that is actually a harmonic. It's the 142nd harmonic of the 10 megahertz clock on the AirSpy, and it's relatively strong. So the only thing we could do was actually eliminate it in post-processing and smooth over it. No amount of putting in filters and ferrites on cables and all that kind of stuff was able to reduce that spur that much. Of course, the total range we're talking here is only a few dB, so it looks really strong here, but in terms that a telecom person would be thinking about, or a ham radio guy, it's only a few dB out of the noise. So really not that strong in absolute terms, but strong in radio astronomy terms. The little hump in the middle is the spectrum produced by a cloud of hydrogen, that's neutral hydrogen, that's in the beam at the time that spectrum was taken. And the blue lines represent the range that we actually care about. And you can also see that there's a considerable slope of about a 1.5 to 2 dB slope in the data. This is just an artifact of the receiving setup, either in the receiver itself or cabling and so on. Again, in ordinary telecom applications, you probably wouldn't care about that. But in radio astronomy, when you're trying to extract fairly precise data, you have to account for that in your data processing. So this is what it looks like after we've processed a little bit. We pull out the RFI, we've desloped it and normalized it and computed a temperature estimate. The sky temperature estimate is actually based on what we already know about the 21 centimeter sky. We don't have an absolute sky temperature reference that we can use, so we just basically scale our data to existing data sets out there. Like, we know what the maximum sky temperature is at 21 centimeters, and we know what the minimum is. So we scale our data according to that. So once we have the process spectrum, we can use it to form pixels in a sky map. So we sum each processed FFT because each individual part of an FFT represents the power estimate over that particular chunk of bandwidth. So the sum is the total power over all of that bandwidth. And again, as I mentioned, we scale it into the approximate range that we know the sky to be at 21 centimeters. So between 15 Kelvin and 100 Kelvin. So the resulting pixels are then processed using Matplotlib. So we do a Gaussian interpolation to produce a smooth image, and we dump that as just a PNG file. And then afterwards, I use GIMP to manually enhance the contrast and the brightness. So there's two different Python routines. Make pixels is the one that takes the raw FFT data and basically grids it into pixels into a 5-degree grid. And then pixels.py turns those pixels into a Matplotlib image. When we move to the new site, our grid size will get smaller because the dish is larger, so our beam width is smaller. So we'll actually be able to produce somewhat higher resolution sky maps from the data. So there's the resulting map, which covers a declination range from about minus 35 to plus 75. Actually, this particular map was to plus 70, but later maps were extended out to plus 75 once we modified the mount slightly to be able to reach that high. And it looks like a heat map like you'd expect from any other bit of scientific data out there. So the bright parts here are the galactic plane. Most of the hydrogen we're looking at is within the plane of the galaxy, at least within the velocity range that our survey is interested in. Extragalactic hydrogen, of course, is further away, which means it's red or blue shifted a lot more, and it would be outside our spectral window for producing these maps. And this is very similar to other maps produced by other amateurs recently with very similar equipment, which is not a surprise. I mean, at the kind of time scales that humans live, the sky doesn't actually change very much. So there's a list of some GNU radio astronomy software. The website CCERA has their own GitHub account. And we have lots of different bits and pieces of software, including the software that produced this sky map. West Virginia University, as I mentioned, has an out-of-tree module for GNU Radio called GR Radio Astro. That was produced in collaboration with the National Science Foundation. And there is the Virgo software. I can't remember the guy's name. He's from Greece. But he's been working on this stuff as well with a slightly different approach. So Virgo is basically like a Python library that you can pull into your application, from the way I understand it, to do radio astronomy-like things. And that's about as much as I know about it, but it is one of the ones out there. There are several others that I don't know as much about, so I didn't put them here. Lots of little discrete tools here and there, both for GNU Radio and other systems. There's applications written for Windows that don't use GNU Radio, and little discrete Python apps and so on to just pull samples off of a receiver and log them, all of that kind of thing. But these are more full blown, and all three of them are GNU Radio based. And I didn't do a sort of introduction to radio astronomy because of time constraints. But for people who are interested in radio astronomy, maybe doing some amateur radio astronomy, I've got some links here. Radioastronomy.org is the website of the Society of Amateur Radio Astronomers. There's NRAO, which is the National Radio Astronomy Observatory in the US. They have a public website that has lots of really good introductory information and even course material, which is really quite good. And I've referred to their course material several times for, getting the correct equations and all that sort of stuff. So the NRAO website is actually really useful, even if you aren't a professional radio astronomer. It's got lots of really good information. There's also the CCERA website. We have a memo series and some documents, and we like to document the activities at the observatory on a reasonably regular basis. And so people are welcome to visit that website and look at our memo series. I think we've got around a dozen memos in our memo series. And of course, I'm always working on new ones. There'll be a new one coming out soon about a FRB project that we're planning. That's a fast radio burst, which some people may have heard of. And we have a project on the go to build a capability for detecting FRBs. And that is it from me.
Okay, thank you, Marcus. Very, very interesting talk. And well, radio astronomy is probably, at least if I've heard it, the most challenging thing, because you need to work with signals that are further that come from further away than possible on Earth, right? I mean, when radio amateurs are talking about signals, okay, Michael, we have a very distinct experience about signals from Antarctica, which is very remote, but signals from a different star, or from different whatever constellation out there, of course, they're way weaker and way more remote, and that's very interesting indeed. So noise and all those considerations are very important there. Okay, so now we've heard 4 talks altogether on statistical applications and statistical approaches to radio spectrum processing. Very, very interesting. Thanks very much, Marcus, particularly now for your talk. And I'd like to open the panel. And Studio Control told me that we have quite a number of participants here now. Hello, welcome back everyone who's been talking before. And very briefly, we have so many experts here in the panel. I've just opened the round, and please raise your questions to whoever you want to raise them. Please go ahead. Who goes first?
I have some questions collected from the chat for Stefan. Stefan, did you read the chat?
Yes.
Okay. Would you like to answer if you have the questions? I can repeat the questions.
Yes, please.
From Mutsinski, when I worked with neural network, the most important thing was the pre-processing. Without that, for my use cases, I did not converge. Have you just trained on the IQ inputs, or was there any other pre-processing?
So I've just trained on the IQ data. I did remove a DC component, and I also normalized the power such that every data has the same power level, and that's it. You can also do something alternative. Many people are calculating a spectrogram. So they form a kind of image. That's what you usually see in a waterfall diagram, and use these images to do the signal classification. And if you do that kind of stuff, it's basically possible to use a neural network that is suitable for image processing. So you turn this signal classification problem into an image classification problem. And you can also have good classificators with that kind of approach. I personally wanted to know if it's possible to do that without that spectrogram calculation, and to see if the network is able to learn discriminative features just from the IQ data.
Okay,
and the
there
results
is an
show that it is
addition.
possible.
There is an addition. So we want to keep the answers mostly short, if possible.
Okay.
Do you think that the training with more low SNR data will improve the accuracy of the for low SNR input data?
So the SNR here in the data goes down to minus 10 dB, which is already
Yes.
very little. So it's important to have some kind of low SNR samples to make the network learn also about noise. Basically, it has to learn that noise is not a discriminative feature to distinguish between the signals. It will definitely help, but there is also a kind of limit. So it doesn't make sense to train a network with like minus 50 dB or so.
Okay, the last question of the same person, Majsinski, I'm not quite sure how to pronounce it. Have you tested your method on a real SDR transceiver?
I've made some basic evaluation. The problem is evaluating a neural network for classification in that application is not that easy, because the accuracy is highly dependent on the SNR you have. So if you have like a real signal, you first have to determine the SNR, and you have to make sure there's no interference and so on. So it's not so easy. But I've made some basic experiments, and it worked astonishingly well. Yeah, so I'm not sure if I can achieve 98% of accuracy, but it's a really useful tool, and I managed to determine modes like Domino X and Olivia, which I couldn't identify just by looking at the spectrum or listening to the signal.
Okay, thank you very much. One question to Markus. Henning Paul, one of our next presenters, which have been active yesterday as well, he said, I'm wondering why exactly that harmonic of 10 megahertz clock is so dominant and not the adjacent ones. Can you give an answer, Markus?
Sure. So the 10 megahertz harmonic is quite strong in that particular radio. The AirSpy radio does have a very strong harmonic at 1420 megahertz. It appears to be very strong, but if you look at the scale of things, the hydrogen signal, if you will, is typically only 1 to 2 dB above the noise floor, and the harmonic of the clock is typically, I mean, I haven't looked at it recently, is typically about 10 to 15 dB out of the noise, which sounds strong, but don't forget that the noise temperature of the front ends of these new receivers is actually pretty low compared to what we might expect in even like a 1990s era receiver.
Okay, thank you. So these are the questions which I collected from the chat. Anybody else?
Well, Marcus
I
had a
haven't
question
observed
for me.
the chat.
Okay, well, Marcus had
I
a
haven't
question for me at the end of my presentation, and the question was, can it always be better? Well, not using this setup. What I figured out is that although we are amateurs and we use an amateur radio band, we've got several types of usage in the band, and it doesn't really make sense to measure frequency band occupancies mixed up between FT8 CW signals and FM or DMR repeaters. So this would scale up if you have a broader piece of spectrum with the same type of usage. For example, a upload frequency of 4G, for example, to see what's actually happening over there. I hope that answers the question.
Yes, thank you. Interesting. Coming back to those distributed approaches. Referring to the topic we've been talking after the end of Adrian's talk with distributed receivers. so I find that approach also quite interesting because also in reference to yesterday's talk from Barry with the ZMQ blocks, where you can not just receive locally, but you're completely free of a local reference. You can distribute IQ samples all around wherever you want. It just depends on the bandwidth. So is that a possible approach also to spectrum monitoring in the 21 centimeter band in radio astronomy? Would you, Marcus, would you do that? Does it make sense to have distributed receivers?
Yes, for a number of different reasons. The local noise environment, of course, will not correlate across multiple sites. So if you're looking for very weak signals, I don't like to use the word signals in radio astronomy because they aren't signals in the usual sense. So yes, distributed receivers make sense just from the point of view of having completely uncorrelated noise floor and therefore improving your sensitivity. But of course, other approaches you might think of as distributed receivers, like VLBI, for example. And in VLBI, you use the geographic distribution to improve your spatial resolution through interferometry. So that's another kind of distributed receiver approach.
Okay, interesting. Yeah, sure. I mean, you can create a correlation between those two signals, and then, of course, distill out what you really want to receive. I mean, if it comes in at one side of the Earth, it should also come in at the other side of the Earth, right? So
yeah, in
it's
fact,
interesting.
With one additionally receiver, you gain 3 decibel.
Well, depending on whether you're using coherent reception or incoherent. If you're using incoherent reception, like you're just correlating the data post-detection, then you only get root 2 for every doubling of the number of receivers.
Okay. Thank you very much. Yeah, well, my batteries of my monitor ran out of power, so we had a little technical issue in the background. Good. Thank you very much. Interesting insight. Any other questions from anyone? Particularly on statistics. Yeah, Jean-Michel, please.
Yeah, the statistical analysis that we've seen are showing what I would call static estimators like spectra, spectrogram, waterfalls. And with respect to radio frequency fingerprinting, where we are investigating dynamic features such as signal rise or signal fall time to discriminate between the real transmitter and the spoofing transmitter, for example. Yeah, I was wondering if these classifiers or artificial neural network could be able to adapt to these time-dependent features of the signal, for example, to detect spoofing and some injected signal in the radio frequency spectrum. If any of the neural network developers has some comment about these time-dependent features.
If you want, I can answer. So basically, DARPA, I think DARPA released a big, large data sets of, I think, thousands of transmitters, Wi-Fi transmitters, and ADSB transmitters also. And there were neural networks that can actually fingerprint these kind of devices. Again, based on minute clock variations of different devices and kind of things. But all those setups are kind of supervised setups. So you need labeled data sets. And if you have labeled data sets saying that, okay, these are these devices, and at some point of time you can do spoofing detection, you can do spoofing messages at least. But the problem is, like, if there is a device that is appearing and to tell what kind of device it is, it might be a difficult task, because that kind of expert knowledge is not there in these kind of neural networks. We just learn from the data and from the data statistics, and if it is not there, that expert knowledge kind of things are not there in their network.
Okay, thank you very much. One more question to Adrian. Does anyone have a question to Adrian? Because Adrian has been staying here, even despite his topic has not been into statistical analysis. Do we have any more questions on distributed radios, particularly with this application? No more questions? Okay. Thank you very much. And I don't see any more questions in the stream. Yeah, we have one more question in the stream. How long did the acquisition last to map the whole sky? Marcus.
That the data represents about a year's worth of observations. Because the instrument is a transit instrument, it can't move in azimuth, it can only move in elevation. So it moves in elevation every 25 hours by a few degrees. And we get lots and lots of repetitions of the same position to improve the signal to noise ratio. So it took about a year to produce the data for that map.
Okay. Thank you very much. That's very interesting. So that's a long time project for sure. And I think radio astronomy is actually a very interesting topic for all radio amateurs. I mean, it's not just about communicating. I mean, we just have those things, those devices standing around, and we're partly consumers. We benefit from solar influence to the ionosphere, but we also suffer from things like Mögel-Dellinger effects and all those funny things that come from the sun. The solar system contains a lot of surprises still, and for sure also in the future. So that's an interesting thing, an interesting field of research. And thank you. Thank you. Big thanks to all of you for coming into this panel. And so this block was very insightful, and I think it's a very active field of research also in the future. I'm looking very much forward next year, and I'm pretty sure we're going to have some talks on this topic again next year also. So I'm looking forward to see you again here next year or in the next years for sure. And then I wish you a lot of fun with the rest of this Sunday. And I'd like to say goodbye to all of you. And then I would like to lead over to the next talk. The next topic is actually one big slot. We have a long, it's that's a couple of it's a pair of topics. We have two contributors who are working together for a student project, and I'd like to present here Luca and Christian, and we've had a long history of presenting student work, student bachelor, master thesis projects, and this is also one of them. And Luca is 21 years old. He's a student of electronical engineering. I have to put on my glasses. Electronical engineering and information technology at the University of Armed Forces in Munich in Germany since 2018. And he's doing his master studies in transmission security. And also Christian is a student of electronical engineering and at the same university, and he's doing the same studies. And Luca and Christian have been working together in an interesting project about the German time signal source on 77.5 kilohertz, which is well known as the DCF 77. And as we have it, we have pre-recorded this video also. And I'd like to ask our studio control team to play the pre-recorded video. Please go ahead.
Welcome to our presentation. Our presentation is about our bachelor thesis, DCF 77, receiving the phase modulated signal with an SDR. At first, I want to point out our structure. In the following, we're going to talk about the DCF 77 signal. Then we are going to explain our hardware configuration and focus on the active selective antenna and the demodulator. Then we will talk about our software structure and the software receiver. And in the end, we are talking about some future projects. The DCF 77 signal is a signal who transmits information about the time and the date. The signal is modulated with two modulations. One is the amplitude modulation, which is commonly used in the most common receivers, for example, in radio-controlled clocks. The signal transmits 60 bits with 1 bit per second. And the amplitude is reduced to 25% of its maximum value to send the bit information. 0.2 seconds stands for a binary 1, and 0.1 second stands for a binary 0. You can see this in the picture on the left-hand side. In addition to that, there is also a minute mark where the amplitude is constant and does not decrease in value. The second modulation is a phase modulation, and in our bachelor thesis, we concentrate on this form of modulation. Therefore, a pseudo-random noise code is used. The pseudo-random noise code takes part in the other 0.8 seconds of the second, where an inverted pseudo-random noise code is a binary 1, and a non-inverted pseudo-random noise code is a 0 binary. On the right-hand side, you can see the bit decoding table, which is used to decode the bits.
Hello, my name is Christian Huber, and I'm going to explain the hardware configuration. So here you can see the block diagram of the complete hardware setup. We have at first the selective active antenna. It contains the receiving ferrite antenna and the bandpass filter and an instrumentation amplifier. Then we have a demodulator. It mixes the signal with a reference signal generated by a local oscillator. And it mixes the signal to a frequency for right frequency for the sound card. And after that, here the digital signal processing would start. So then I explain the antenna. At first, we have two inductors which we have to construct we have to construct a ferrite antenna, a receiving ferrite antenna, and an inductor pod core. This pod core is we need for the bandpass filter, and both of these inductors should have inductance about 1.5 millihenry. We also need for the filter design some properties. For example, the self-capacitance. We can measure the self-capacitance with the resonance frequency of the inductors, and then we can calculate it. And we have to, we need the value of the quality factor. The quality factor we can measure with that measurement. You can see here the signal generator, which should have the frequency, the resonance frequency we want to have. In this case, it's the 77.5 kilohertz. Here we have the resistor, the self resistor of the signal generator. And after that, we need 150 ohm resistor more. And here is the inductor. Here the resistance of the inductor. And here we need a capacitor with which the inductor have a frequency, a resonance frequency of 77.5 kilohertz. So, and with a potential divider, we can calculate this resistance, and then we can calculate the quality factor. The quality factor is over 200, and that's a good value for both inductors. So here you can see the equivalent circuit diagram for the bandpass filter. So we did a differential version of this filter because a differential filter has the advantage that there is no less failure prone, and it should have a bandwidth of 2.5 kilohertz for our signal. And you can see here two resonant circuits. One is based on our ferrite antenna. So you can see here the inductance of the ferrite antenna, and here the resistance, and here the self-capacitance. The same is here in the second resonator. And there we have a capacitor, and that's the same capacitor we used for the quality factor measurement. And then we need two coupling capacitors, and these four capacitors are implemented as trimmer capacitors because we need to adjust the filter accurate to the resonance frequency. Okay, here you can see the instrumentation amplifier and the whole circuit of the active selective antenna. Here is the bandpass filter with all values calculated. Both ends of this bandpass filter are amplified. At the first step, we have an operational amplifier which amplifies the signal, and between them we have a potentiometer, and with this potentiometer we can adjust the amplifying factor. You didn't see it here in this circuit because we want to simulate here resistance of this potentiometer of nil. And after the first step, both signals ends in a differential amplifier, and because both signals are phase shifted and one signal is inverted, we have an amplifying factor of 2. This last operational amplifier is for symmetry purposes. Here you can see the voltage supply band, and we want to use a 5-volt USB connection, so we have to sift the voltage at first with those capacitors mainly. Then you can see here voltage potential divider. So we have here and here a voltage of 2.5 volts, which we need for the operational amplifiers for their operating point. Here you can see the whole setup for the active selective antenna. Here you can see the receiver ferrite antenna. Here is the bandpass filter, and here are the 4 trimmer capacitors. And here is the pod core. And on this side is the instrumentation amplifier. And here the potentiometer, where we can adjust the amplifying factor. Here are some measurements of the filter. Here we have the phase response. So you can see here a linear phase response. The markers are, the marker in the middle is the 77.5 kilohertz marker. And the other markers are for the 3 dB bandwidth. So that's 1.5 kilohertz difference between that markers. And in this, so we have here a nearly linear phase response. Here you can see the magnitude response. The markers are on the same place, and it's nearly symmetric, so it looks like the magnitude response of a bandpass filter should look. Here we have at last the noise measurement. The marker here is at 77.5 kilohertz too, and here we have the highest noise because we filtered and amplified that frequency, so there should be the highest noise. And for this measurement, we replace the antenna with an inductor, because if we made this measurement with the antenna, we would get some noise from outside, and that's not what we want to measure. We want to measure the self noise of the circuit. So yes, we put that inductor in there, and that's the dominant part. That's the dominant self noise of the whole setup, of the whole hardware setup. The demodulator don't have such relevant noise, self noise. So it's the main self noise of the whole hardware setup.
Now we are going to talk about the demodulator. As you can see in the picture on the left-hand side, we get our received signal, E from T. And yeah, it is split in 2 branches. On the upper part, there is a mixer, and above it, darunter, was heißt darunter? Below, yeah. And below it, you can also see a second mixer. The mixers are getting the local oscillator signal which we use to mix our received signal. In the one branch, we got a cosine signal, and in the second branch, we use a 90-degree delayed cosine wave, so we could get a minus sine wave. Both signals run through a low-pass filter, so we can put it into the sound card, which is our analog digital converter. In the end, we got an I signal. The I signal, we get the I signal when we mix our received signal with the cosine, and we also get a Q signal through the mixing with our negative sine wave. Yeah, how do we mix two frequencies? Here are some quick math operations. We want to get our signal S from T by multiplying our received signal E from T with our local oscillator signal. The received signal is, as I mentioned before, a cosine wave at a frequency of 77.5 kilohertz. That's why we call it DCF77. And the local oscillator signal is, in this example, a random frequency. And we need to think about the frequency the local oscillator needs to mix our frequency in the right, to the right frequency, so the sound card can sample the signal. If we multiply it, we got two cosine waves, and the cosine wave has in the frequency dimension always two directs. And because of the two cosine waves we got here, we also got four directs. Yeah, as you can see, mixing two signals, when you mix two signals, there is a sum and a subtraction. So you can see the directs in this picture. On the left-hand side, of course, also the negative frequencies. In our bachelor thesis, we only want to use the lower frequencies because only the lower frequencies can be sampled by the sound card. So how do we generate the local oscillator signal? Yeah, as I mentioned before, the sound card has a sample rate of 48 kilohertz, and with the Nyquist theorem, we need a frequency in the time domain for our cosine waves from 0 hertz to 24 kilohertz. In this bachelor thesis, we used a 16 megahertz quartz oscillator. Therefore, we used a binary counter and flip-flops to divide this frequency in to a frequency we could use to calculate our frequency for the sound card. Yeah, in this case, we got 8 divider, so our frequency is at 62.5 kilohertz. And in the end, our cosine frequency is at 15 kilohertz. Here you can see a small block diagram about the local oscillator frequency. We are starting on the left-hand side with the quartz oscillator. We used CFPS minus 72 for it. And we get our 16 megahertz at this point. The binary counter divides this frequency to 250 kilohertz, and then it goes through a dual D positive edge triggered flip-flop for receiving our frequency we need. But how do we demodulate? We use, in this case, the Taylor mixer. This is a very special demodulator. On the right-hand side, you can see a very simplified picture of the Taylor mixer. We got here our signal, and it goes through a switch, and here are 4 switch stages. Behind the switches are capacitors. The capacitors also form with the resistance of the switches an RC low-pass filter. And these switches are very important for us to generate our I and Q signal. 2 branches are filled in the input of an operational amplifier. In the case for the I signal, you can see that we need the null degree and the 180 degree sampled signal. And to form the Q signal, we put up the 90 degree and the 270 degree signals. So we got our mixing with the cosine for the E signal and the minus sign for the Q signal, as you can see here. Yeah, in addition to that, we use our clock frequency to switch, and we got our mixed frequency at 15 kilohertz because there's also the low pass filter. To simulate the Taylor mixer, we used LT Spice. Yeah, in this picture you can see the Taylor mixer and the rest of the setup. The Taylor mixer only contains these 2 flip-flops here. These are the switches. Behind the switches you can see the capacitance, and here's the first amplifier stage, which is also important for the Taylor mixer. We also used a second amplifier stage, so our signal is stronger. Yeah, in the left corner you can see a bipolar transistor. It is used as a source follower, and we need the bipolar transistor for our amplifier and all other integrated circuits, because we only have a single supply voltage. We use this bipolar transistor as a source follower because we want to form our filter with the resistance of the switches and the capacitance. We have also another resistor R4 here, and we don't want the output resistance of this bipolar transistor to be important for our filter design, and therefore we used a source follower. This leads me to the next point, the filter design. It is very important that both branches, the I branch is the upper part and the lower part is the Q branch, and between these 2 branches it is very important that the filter phase is equal. This is very important for the efficiency of the IQ demodulation. Also very important is that the amplifier stages have the same gain, because it could be inefficient if the Q part or the I part is stronger than the other part. But I will explain that later. Yeah, at this picture you can see the power supply setup, and then very important idea was to separate the digital part from the analog part to make sure that no high frequencies influence one of these parts connecting through the ground. In addition, it is important to say that the ground should also be connected. Therefore, we used an inductor here, so we have no problems with high frequencies. Here's a picture about the layout. As you can see, here is the digital part. There's the quartz oscillator, the binary counter, and the flip-flop. Here is the inductor I mentioned before. The bipolar transistor is connected to the analog ground, and here is the analog part. Here are the switches. These are capacitors, and on the right hand side you can see it from below. Now we are going to talk about the simulation and the measurements. On the left hand side you can see the simulation. Very important is that the green signal is the cosine and the red signal is the negative sine wave. On the right hand side we can see the measurement, and if we compare both pictures we can see that it was successfully. Very important is also the 90-degree phase delay for the IQ demodulation. In this picture you can see the complete hardware setup, starting on the right hand side with the antenna and the blue box with the bandpass filter and the instrumental amplifier. In the silver box is the demodulator, and on the left hand side you can see the sound card. Everything is on an USB port, so you can connect this with your laptop or computer and you are mobile and can choose where you want to receive the signal. In this picture you can see the signal, the process of the signal recording. To choose the antenna direction we used a program named Audiometer. It is also linked in the literature, so you can use this link later if you want to use the program. You can see a clear peak at 15 kilohertz. This is very important. In the lower part of the picture you can see the recorded signal. The amplitude was very good. We got a nice signal to noise ratio. So you can also see the amplitude modulation. It was important to record 2 minutes. So there is the possibility that 1 full minute is recorded. Now I am going to talk about the software structure. Our two signals, the I and the Q signal, are now sampled. That's why there's an N and not a T. These two signals get added, then they got multiplied by a complex phasor, so we can transfer it into the baseband. Then it goes through a low-pass filter. Then we use a cross-correlation with the pseudo-random noise code. Then we use a differential phase corrector. After that, we can interpret the bits and also evaluate them. So why do we use I and Q? If we focus on the I signal, as I mentioned before, we have a cosine wave at 15 kilohertz, and in the frequency domain, we can see two directs at -15 and +15 kilohertz. The Q signal with the negative sine wave has an imaginary spectrum. So in the frequency domain, we can see a positive direct at -15 kilohertz and negative direct at 15 kilohertz. If we now interpret the Q signal as imaginary, we add a J, and therefore the Q spectrum goes vice versa. If we add these two signals, the IF and the JQF signal, we only got one direct at 15 kilohertz, and this is perfect. Now I want to talk about the baseband transformation. We are now in this part of our software structure. We use our complex phasor to shift it into the baseband. Shifting it into the baseband in the time domain is nothing else than a convolution of two directs in the frequency domain. In the picture on the left-hand side, you can see the received signal, and on the right-hand side, the shifted signal. Another important part you can see in the left picture, the IQ demodulation efficiency. We have our direct at 15 kilohertz, as I mentioned before, but we can also see a direct at -15 kilohertz. Now we can calculate the difference between these two directs, and we can see that there are something like 45 dB difference, which is very good. Now I want to talk about the low-pass filter. It's a finite impulse response filter. We choose a very low -3 dB frequency of 600 Hertz. So we got a bandwidth of 1.2 kilohertz. On the right-hand side, we can see the impulse response of this filter, and the phase is also linear at this point, which is also important for our IQ demodulation. In this picture, you can see the filtered signal. I think it's common for everyone. We want to reduce every noise outside of our filter, and it was good.
So after we filtered the signal, we do a cross correlation between the signal and the pseudo-random noise code. Here you can see this code once again. And this code is in the signal too, because it's modulated with it. And it contains the information. So a non-inverted version of this code represents binary nil, and an inverted version of this code represents binary 1. So when we made this cross correlation, when we did this cross correlation, we detect such this code in the signal. We get a maximum, and in this maximum we can in this maximum there is the information we want. So there is a problem, because when we look at the formula of the signal, we have at first a coefficient multiplied with some complex rotating phases. The first complex rotating phasor you see here belongs to the carrier frequency. We mix the signal in the baseband, so the carrier frequency is not longer relevant. Here is the complex phasor with the random noise code. There is the information, and here we have another rotating phasor, and that represents the transit time phase shift. That's a problem because this angle leads to a phase shift of every maximum we detect. Here you can see the maxima of 2 minutes received signal, and you can see every maximum is shifted. And that's a problem because when we want to extract the information, the phase difference is important. So we take the first maximum we get, we shifted it to the real axis, to the positive side of the real axis, and every maximum we detect the angular difference, and we shifted it about this difference back to the real axis. If we detect angular of 180 degree, like here, we know that there has to be a sign change of the bit. So we know, or the sign of the bit has to be negative in this case, when the sign of the bit before was positive. So this maximum gets to the negative real axis. So we have, at the end, we have this diagram. We have some maximas on this side, a positive real value, and some negative real values. Then we have to interpret the sign of the bits, because we cannot be sure if the positive sign of that bit represents binary 1 and this side represents binary 0. So we have to compare it to the actual time that we can find out what's the right interpretation. So, and when we did this interpretation, we get such a diagram. There you can see the 120 seconds, and so we get 120 maximas, because every second we get such a maximum. And why do we record 120 seconds? Because we need to receive 1 whole minute. And the start indicator of a minute, you can see here, it's a sequence of 10 positive maximas or binary 1 bits. And that's the sign how we can interpret the bits, because if we have a sequence of 10 binary nils, we know we have to change the sign of the bit. And once we have this start indicator, we evaluate the other bits with this tabular you will see in one of the first slides. So the first bit nil to bit 9 contains the minute information. Then we have some bits which contain none information. Then there are some special bits like a change from summer to winter time, and then we get the time information. And at the end of every part of such time information, for example, for the minute part or for the hour part, at the end we have a parity bit. And this parity bit complements to an even number of binary ones, the sequence. And it's an indicator which helps to assess if the information which we evaluate is correct. We don't know where is the mistake, but we know if there is a mistake. And at the end, when we made this bit valuation, we get the time information, and so it looks at the end of our program. This diagram of the signal you see here, we receive at 16 o'clock 34 minutes at Monday, the 15th of February 21. Okay, that was the project. Then I want to talk about some future projects we have on this topic. At first, we want to implement a signal to noise ratio estimator, and with this estimator we can see how good the signal quality is, and we can make a new program which contains all the parts of the program before until the cross correlation, and then we can make this signal. We can implement the signal to noise ratio estimator, and so when we do that every second, we have an indicator how good the signal quality is, and we can adjust the antenna in the right direction and compare it, which is the right direction for the best signal quality. Another project is that we could implement a bit error code in this program, and with this with the bit error code we can detect how good our program performs with a self-generated signal, and the signal can contain noise, it can contain interference, and so we can compare our program, our receiver, with other receivers and see how good it performs. So that was our project on DCF77.
So, thank you very much for this very interesting talk, Luca and Christian. And yeah, this is an interesting bachelor thesis. And I think not all bachelor theses are so interesting that you can make a talk at such a conference. But this is really a nice example. And for sure, absolutely interesting also to learn how to go into those topics and actually, well, it's a good proof that things really work and you have a great success with your project. So that's very good. I don't see any questions here in the chat. Michael or Jean-Michel, do you have any questions?
Jean-Michel, you have to enter the microphone. The microphone is off.
Apologies. Thank you. Yeah, I wanted to congratulate on the excellent work, because I did this kind of work 3 or 4 years ago, and you identified all the issues that had to be challenging in this project. You found the IQ imbalance issues, the phase which is not 90 degrees, the magnitude, amplitude of the signal which is not the same. You found the fine frequency offset correction that you needed to introduce before cross correlation. So definitely you address all the main issues of this project, and it's an opportunity to take the best use of DCF77, because even though the phase modulation has been introduced in 1988, I'm only aware of a single commercial receiver using the phase. And indeed, even my watch, which is a DCF77 synchronized watch, is only using amplitude information. So I hope that at some point people will end up using fully DCF77. It's not a cheat question. It's a real question that I wanted to ask. Is at the beginning, you spend a lot of time showing all these bandpass filters made of capacitors, inductors, this huge inductor of a millihenry, and then you've got your IQ transposition. And after that, you learned how to make a mixer in the digital domain, how to make a filter in the digital domain. So I wonder, what is the benefit of all this analog processing front end, and why not digitize as early as possible, possibly just a coarse frequency transposition, and then using the benefit of digital signal processing to implement the filter and the frequency transposition, which I believe would have made the whole setup much easier to develop, which is actually what Sentinel radar satellite is doing. They have a coarse frequency transposition and then a digital transposition using the IQ ideal property. So maybe you have a comment on this analog front end that you've developed.
Yes, I want to answer on this question. In our bachelor thesis, our plan was also to focus on the whole study. Yeah, we want to implement very much points of our bachelor study, and our professor thought it would be a good idea also to take part in the analog world of electrotechnical engineering. So we have much more knowledge we can introduce in our bachelor thesis.
Excellent. Thank you very much.
May I add the question? Did you had a look on how is the energy consumption of a digital version compared to an analog version? For the filters?
No, we didn't have a look on it.
Okay, I can understand that a professor has the goal to teach everything of electrical engineering, of information technology, and therefore the project is divided into an analog part and a digital part. It's the same solution I would suggest to the student.
Very good. We have another question now in the chat. Yes, Florian, I saw it. But Jean-Michel asked this question. We have a question from Erwin Sally. Did you compare the phase results to the other way of getting the correct time under AM? Did you compare the phase results to the other way of getting the correct time under AM demodulation?
Well, we only focused on the phase modulation, and the amplitude modulation was just a funny thing besides the phase modulation. So we didn't compare the resolutions.
Maybe I can give a hint of my past investigation on the topic. I investigated the phase modulation or phase cross-correlation of DCS77 for ionospheric delay measurement, and we observed 60 microsecond, let's be conservative, 100 microsecond accuracy on the time delay, which allows you to see the D layer vanishing in the evening. And typical amplitude detection would give you a millisecond. So the phase demodulation, the phase cross correlation will give you an improvement tenfold with respect to amplitude. If you just want to keep your watch within 1 second, amplitude and phase is not going to make much of a difference. If you want to look at the physics of atmosphere and ionosphere using the VLF signal of DCF77, the tenfold improvement will be definitely a huge gain.
May I ask, Jean-Michel, do you know of any application for ionospheric research to evaluate these differences in phase demodulation of long wave transmitters?
I would say that now that you have active radio sonde measurements, it's just, it's a bit like passive radar. I mean, it's hitchhiking existing signal that I enjoy. And if you're really into research, then you would just be using one of the radio sonde radar already existing. One topic that I found fascinating, and I'm definitely not qualified to interpret its validity, is the interaction between lithosphere and ionosphere. It has been identified that prior to earthquakes, there would be some disturbance that could be detected in the ionosphere. It has been seen in Indonesia. It has been seen in Japan. So it seems that there is some sort of interaction. And that's the reason why I have my DCF77 receiver running 24/7 in the lab, just in case something happens one day. And I've been collecting these DCF77 signals since 2017. Nothing has happened since. But this interaction, lithosphere, ionosphere, I find it fascinating. And that's one of the reasons I keep on looking at these signals.
Thank you very much. Maybe you know the activity at HAMSci. This is a discussion group of some US hams and some European as well. And they are talking about how is the interaction between the ionosphere and how can we measure it. And there is a frequency deviation. It could be one signal for evaluating the ionospheric height and the levels of the ionosphere. Okay, thank you.
So I think the discussion emphasizes how good the project is and the high quality of what you're working on, the perspective of what could be used when you finish your bachelor thesis, and that this work is final. You see that there's a lot of perspective on this work.
Well, Luca and Christian, are you going to install your research as kind of a permanent project at your university? Well, I mean, collecting delay information is actually quite interesting, and of course, you could probably correlate that information with the kind of data Jean-Michel is collecting, right? I mean, the DCF77.
Yes.
Please go ahead. Yeah.
I think that may be possible, but I don't know what our professor has planned for the future. But we must graduate at the university at first. We want to do our Master of Science now, and this is the first project we have to finish.
Very good, of course. Yeah, sure. That's important. Well, I think if you compare,
Nice.
yeah, very good. Yes, the DCF77 is somewhere around Frankfurt. So, Jean-Michel, how far away are you from Frankfurt, roughly?
450 kilometers east, which is very nice because München is to the south, so that would make a very nice triangle to do this kind of analysis.
Yeah, exactly. Exactly. So the distance is more or less generally the same. So the runtime of the signal should be more or less the same, and the question is where the reflections take place, and whether the reflections are directly on the path, or those reflections come from a different angle. That's all highly interesting, and that could be some additional research on of what you've done in the past. And I find the term hijacking pre-existing signals, I find that really good. So of course, yeah, there are lots of signals around there, and you can deduct a lot of insights from these signals, even though they are not meant for those insights. They're not generated for that purpose, but they can give you some really really astonishing new insights. That's very good, very good kind of research, a very reasonable kind of research, particularly because it doesn't cost you anything. You won't need to install transmitters, you won't need to install atomic clocks or whatever, but you can do a lot of interesting things from that. So very, very good. Okay, so if there are no more questions in the chat, I don't see any more questions. Very good. So thank you very much for this
Thank you.
very nice, very insightful talk. And Christian and Luca, we wish you also a lot of success in your further studies. And greetings to your professor, and to Florian, who's obviously following the stream also here in the chat, because he raised some questions and gave some comments. Thank you very much, and see you again soon. Thank you. So we have another talk now from Henning Paul, who's relocated to the garden. And dear audience, you've seen Henning Paul yesterday, but for those of you who have not been here yesterday, I would like to present him once again. So Henning has been a hardware hacker since his childhood, but gained interest in wireless communication during his diploma and PhD studies in information technology at the University of Bremen. And having left academia for the industry a few years ago, Henning decided to intensify his free time activities on software-defined radio, and is currently waiting for his amateur radio novice license examination to be finally able to transmit and not be restricted to receiving only. Well, that's about Henning. So our speakers just before are actually a good example of what we've done together with the academia, and I think this is a very, very good example that there is a strong cooperation with students and PhD students, and that we're giving students and PhD students and also research a space to present projects and to interact. And as I mentioned yesterday in the very beginning, I'm also very glad and very happy that we have that very good and very fruitful cooperation with the European New Radio Days, and with you, Jean-Michel, and your colleagues particularly. So here this talk is going to be about bridging the gap between scientific SDR and amateur radio. So there is kind of a gap, and this is also the reason for us being here, and the reason for the existence of the SDRA. And in the introductory slides, Jean-Michel, you wrote also that this is also one of the important ideas why the European New Radio Days came into existence. So that's generally a good point for us to be around. And Henning made up his mind a little more into this direction, and for that reason, I would like to hand control over to our video team and to play the pre-recorded video. Please, video team, go ahead.
So thank you very much for the kind introduction. Welcome to my talk today. My name is Henning Paul, and I will tell you a little bit about scientific uses of software-defined radio from a perspective of a former scientist at a university. So what will I be presenting today? First, I will give a short introduction, and then I'll go into the technical details. So what's the difference between software-defined radio and, let's say, scientific communication demonstrators? Software-defined radio has been used by hobbyists for like 10 years, approximately by now, at least in the mainstream. This was the advent of the RTL SDR, which was the major breakthrough for software-defined radio for hobbyists. But actually, the concept of software-defined radio is known longer, for at least the 1990s. But back then, it was only used in research and development. So means big communication companies, for instance, and also the academia, means universities and research institutes used software-defined radio techniques that you would call software-defined radio today, but usually go by the name of communication demonstrators or hardware demonstrators or the like. Back then, this was a very costly thing to do. You needed very expensive hardware, and because of that, universities often resorted to own designs. They designed their own transceivers and signal processing devices and such. And what I would like to tell you today is what was used in the 2000s at the Department of Communication Engineering, the ANT at the University of Bremen. I was a researcher there for 11 years in total, and I had to do with yes, actually all of these hardware demonstrators that I will be showing today. I used those more or less intensively. So that's why I would like to start with the first system, and I'd like to give you a quick motivation on what was the purpose of hardware demonstrators. And actually, there, of course, was always a desire to evaluate communication algorithms that had been developed in industry or in academia under somewhat realistic channel conditions, means propagation conditions, and also include all the hardware non-idealities that you usually have. And that's the reason why we did all this stuff back then. And topics that were of particular interest back then were in particular OFDM, CDMA, and very exciting topic, multiple antenna systems. And of course, as a researcher, question is what frequencies should you use for your studies? And the best solution would have been communication bands like 2G or 3G bands, but what usually was common practice back then is that you use the 2.4 gigahertz ISM band. Of course, this is only a semi-legal solution because you can't really use the totally legally these bands, but usually when you resorted to low transmit powers, well below powers that were usually used for Wi-Fi systems, you wouldn't run into problem by doing so. So the first demonstrator that was developed at the ANT was a single antenna hardware demonstrator, which was the result of a diploma thesis around 2000. There were two incarnations basically of the system. There is the modular version that's shown here in the middle of the picture, and there's the standalone version with some user interface, which is basically both the same technology. I would like to concentrate on the middle one here, how this looked like and what the capabilities of the system were. This was a modular system, means the baseband interface and the transceiver were separated, and they were interfacing with each other using SMB connectors. So it means the baseband was the analog baseband was the, say, division line between these two devices, to the systems. And this was a project by a former colleague of mine, Thorsten Hase. He did all this as a diploma thesis in 2000, and of course he had support by our lab engineer Heinrich Masemann, Delta Bravo 7 Bravo Papa, and it was more or less a joint project of these two guys back then. So what does this system contain? How does it look like technically? So first, we look at the modulator-demodulator unit. Maybe this is the part that's more interesting to the ham radio operators. This system, this module used an Harris chipset, which was usually originally designed for Wi-Fi 11.b, and consisted of 3 chips, which is the main IQ modulator, external VCO, this one modulated onto intermediate frequency, and then there was the mixer that actually did the up conversion then to 2.4 gigahertz, and a power amplifier chip after the mixer. And we had this neat little case here, with some rudimentary user interface. Yeah, you could just select one of 4 channels and toggle between TX and RX. Yeah, this was a half duplex system. And then we had the analog baseband interface here, which would then interface with the next device that I will show in the following, which was basically this one here. This is the core of this device is in Xilinx FPGA, Vertex E FPGA, with static RAM as a FIFO, and some interface chip CPLD that was used for the parallel port interface. Yeah, you might smile a bit, but back in 2000, the parallel port was still, for most applications, the port of the interface of choice. Yeah, USB was just new back then, so a lot of systems used a parallel port back then as an interface. Yeah, attached to this FPGA were AD converters and DA converters, just like you would do it today. Yeah, it's not a difference. So today you would do it exactly the same. Here we have parallel DAC and parallel ADCs, dual channel DAC, and 2 single channel ADCs that did the digital to analog or analog to digital conversion, vice versa. And we had a clock generated chip on this device, which is not that different actually from the famous SI5153, or the other way around. I can't remember that. It's a clock synthesizer that's ubiquitous in every today, more or less in every application today. And this was an, say, early predecessor from a different company that did basically the same, synthesizing the sampling frequencies with some digital interface. Yeah, so I guess SPI or I2C or something like that. Yeah, and then on the PC side, we had this little graphical user interface that Thorsten wrote back then, which, yeah, transferred binary files, IQ files, containing the samples to transmit, or vice versa, the received samples over the parallel port. Yeah, just byte-wise, and then filling the FIFO of the baseband board by doing so, or the other way around, transferring the IQ samples from the FPGA's RAM buffer, the static RAM buffer, into the PC. And yeah, it's more than 20 years old, this technology, but I guess not that different to what you are doing today, for instance. Yeah, and what could you do with this kind of device? And yeah, you could, for instance, implement a GSM transmission. Yeah, you know GSM, 2G mobile phone system, mobile communication system. And what other colleagues of mine did back then is implement all the physical layer of GSM, the GMSK coding, and the forward error correction, and synchronization, and the channel estimation, all the like in MATLAB, and then used the parallel port to upload then a frame, a communication frame, into the transmitter, and transmit it and receive it vice versa with the corresponding receiver, and then have it offline processed then in MATLAB and at the receiver side. And back then we used these demonstrations often in the lectures to show the students how a practical communication system would operate. For instance, here in this picture, you see the complex envelope of the transmit signal. Yeah, it's GMSK, so that's why it's a circle. And then, for instance, you could have a look at the transmit spectrum. Yeah, I guess the power spectral density of the transmit signal, the time domain signals at the receiver side. Then, for instance, the result of the channel estimation in the Z domain, as well as in frequency domain, and the impulse response. And for instance, also the impulse response over time, which is of particular interest, because when you're doing mobile communications, usually you have fading channels, meaning the channel vary over time. And you could use back then, 20 years ago, the visualization features of MATLAB to illustrate how the impulse response would behave over time. Or here in this case, the frequency response. Yeah, you see the notches there from multipath propagation, the zeros and the frequency response, and how these would then change over time. This is what the colleagues used back then. Another application was Hyperlan 2. Hyperlan 2 is what later became 11.A Wi-Fi. It's Hyperlan 2 was the OC part. It's not an IEEE standard, it's an OC standard, and it never actually was accepted in the industry, but the technologies were then later used in 11.A and then also later in 11.G. Yeah, it's an OFDM-based Wi-Fi system, and the colleagues wrote a demonstrator in MATLAB to transmit these OFDM frames. Here you see, for instance, I and Q and time domain at the transmitter side, and here the typical OFDM spectrum of one of these frames. Think of 11.A or 11.G Wi-Fi frames in this case. And then the whole transmitter was implemented to be operated then in non-real time. And this is, for instance, the output of the cross correlator, which does the time synchronization. And for instance, there's the receive spectrum and the result of the OFDM channel estimation. Yeah, you can nicely see all the individual subcarriers and how they are attenuated by the actual frequency response. Yeah, and for instance, in the end, the constellation that results then from after the equalization of the OFDM transmit frame. Yeah, so this was 2001. This demo. This was basically when I joined the university. This was what the researchers back then showed to the students, for instance, the first semester students, as a teaser of what is actually done in the Department of Communications Engineering. Yeah, then only 1 or 2 years later, then multi-antenna systems became big in research. Means using multiple antennas at once, both for transmission or for reception, in order to do fancy stuff. And that's why the colleagues decided to extend the system to a multiple antenna systems. And this was the result then back in 2002. This is basically the system you saw before, using 8 coherent channels. Yeah, all the channels are fed from the same local oscillators. They are synchronously digitizing the ADCs. And this was a very, let's say, groundbreaking thing, because there were not many universities in Europe that had something like that demonstrator able to do a coherent multi-antenna transmission. And this again was a project by Thorsten and Heinrich, and it's called MASI, yeah, as an homage to Heinrich Masumann, the colleague that our lab engineer. And it's just a refreshed multiple channel version of the demonstrator we saw before. We had different modulators, demodulators. This now is a simplex system. This is not capable of doing half duplex anymore, but this simplified the design significantly. That's why the colleagues used this simplex system. Sampling rates were up to 50 megahertz, so this is quite whopping back then. But of course, there needs to be a drawback. Drawback is this thing only had USB 1.1. Yeah, I guess you remember 12 megabits per second. So this definitely was a non-real-time system, I say offline processing, because you would then, at the receiver side, for instance, fill the FIFOs. Yeah, means 1 mega sample per channel, and then you would use the USB 1.1 interface to transfer all the RAM buffer contents into the PC and do the MATLAB processing. And this could take a minute or two. It was not too fast. It was, but it was okay, yeah, for the time being. Yeah? And this is the device that I did a lot of research with. I did my Studienarbeit with this on this box. I did my project thesis on this box, and I also my diploma thesis was heavily supported by measurements done with this box. So this is the one that I can relate with the most, this device. And now a little bit more of technical details on what contains this box. You see, for instance, this is now one of the receiver boards. It's still a Vertex FPGA, and still it's a static RAM that's attached to it, and we still have two separate ADCs, so it's not that different to the single channel version. But what's different is the bus here. Yeah, so this is a 8051 Intel microcontroller bus. So Thorsten and Heinrich decided to use an 8051 with USB 1.1. So this basically, you would then use the 8051 microcontroller bus to transfer all the data. Yeah, and this is what this connector back here, this DIN connector is connecting to. It's an 8-bit parallel bus, straight from the 80s. The modulator, or a demodulator in this case, because it's a receiver board, is directly located here, and you should imagine some like a sheet metal box over here. Yeah? This is just removed for the photograph, so it's properly shielded. We have some shielding cage over the area here. And the block diagram basically directly represents what's contained on this PCB, and you can have a look at the slides then yourself and try to find every device in the block diagram also on the PCB. So next slide. Yeah, now what's the purpose of this box at all? So yeah, you can do MIMO measurements, means multiple input, multiple output, means you transmit over several antennas, you receive with several antennas. For instance, you transmit over 4 transmit antennas and you receive with 4 receive antennas. That means you get 16 transfer functions in total. And you can see these here on the slides. From every transmit antenna to every receive antenna, you have a transfer function, and there are 3 different colors here on the slide. This is just 3 different trials. Yeah? So it means the channel has changed in the meantime. So this is why the channels look a little bit different. And you can see the 16 megahertz of bandwidth, 60 megahertz one-sided. It means 32 megahertz of bandwidth that every channel has here in this demonstrator. This picture is taken from a paper that was written by Jürgen, Delta Charlie 3, Bravo Whiskey, and my former prof, Professor Kammeier, and this was a joint paper in 2003 by these guys. Yeah, we then later did some extensions on this system, and here's one more example what you actually could do with this kind of technology. One antenna was transmitting data, and then we have received with 4 different antennas. We get 4 different replicas of the received signal, and on what you see in A is the signal on receive antenna 1, on B is the signal on receive antenna 2, and you see basically you can only imagine that this was a 256 QAM, and by combining these 2 signals with the correct phase shift and correct scaling, you end up with the result here in C. Yeah, I can almost guess that it was some kind of QAM. When you now combine the receiver signals from all 4 antennas, you end up with this signal constellation. Yeah, it means multiple antenna systems, receivers will give you an SNR gain. Yeah, you combine the different replicas of the system, different replicas of the received signals in order to improve your receive SNR. I will give an application to amateur radio in my other talk, so it's a quick just advertisement for the for my other talk where I apply something like that for continuous wave signals. Yeah, extensions to this system. Yeah, we again modded the system into a half-duplex system by using some relays and an LO splitter, and also did some measurements. If you're interested in the results, here are the links where you can find the full papers from these results. Yeah, and that's basically what we did with this demonstrator. But of course, over time, you get your, you want more from your hardware, and this is why we moved to a real-time capable system. I will only give one slide on this system because this was a commercial off-the-shelf system. We didn't build it ourselves, so this is why I would like just to give a short wrap-up what the system actually, how it looked like. So it was a compact PCI system from the shelf containing ADC and DAC cards with FPGAs. There was a 4-channel modulator-demodulator that would interface with these ADC and DAC cards. And there were also a card with a FPGA as well as a digital signal processor, one where you could also do some real-time processing of received signal on the DSP in connection with the FPGA. Yeah, and it also had the clock source, which was GPS disciplined. This is particularly nice because by doing so, you didn't need to hard sync receiver and transmitter with a cable. Yeah, when you just let both of them synchronize to GPS, and then you have a synchronous system from the transmitter to the receiver. So this is why we also chose the clock source board in this system. Yeah, so this ends my talk. So what did you see today? Yeah, I showed you a little bit on what hardware we used back then in university for demonstration purposes. And as a teaser, in my next talk, in the follow-up talk, I will show you what I did since then. So the hardware designs I did on my own, which were, of course, heavily inspired from these hardware demonstrators that I've just shown you. So I thank you very much for your attention, and I'm happy to answer questions in the Q&A.
So thank you very much, Henning. Very, very interesting. Once again, all our talks are interesting. Really, very good. Excellent. Well, what I find most interesting about that is that you're demonstrating that you can indeed produce modern digital signal processing electronics yourself, and you can really do that also as a hobbyist, also as a vocational engineer. And you've been doing that. Okay, you have a certain background. You also do that in a professional domain, but it is possible to take schematics from application sheets and put them into KiCad and try them out and get them running. And that's really an interesting signal to the entire community. You can do that. You're not limited to analog stuff, but you can really also do signal processing yourself. You can create PCBs. You can do all those sorts of things, soldering, FPGAs, and so on. This is definitely possible. There are hurdles. It's not super perfectly easy, but it can be done. And particularly in a university environment where you do have prototypes, you don't have a big production of a big series of devices, but also for small amounts of devices. This is definitely feasible also in a financial range which a private person can cover, which is good, which is makes a lot of hope and a lot of it inspires you, inspires many people around there to try out those things themselves. Very good. Okay, thank you very much for this insightful talk. There has been some interaction in the talk. In the chat, but I think these questions were discussed.
Yes, I think it was about the previous talk.
Yes, it was about the previous talk. Yeah,
it's on the previous talk. Yes, it is. I have controlled it, Markus. There is nothing now in the talk about Henning's talk.
Yeah. Okay.
It was just to say a historical wrap up. Yeah. So all the new content was in my talk yesterday. This was just say an entertainment talk today about what has been what has happened in the history up
Yeah.
till now. Because when software defined radio became big, like 10 years ago, I was very excited because now I could do all the stuff that we've been doing in the lab with rather expensive hardware. Now with cheaper cheaper hardware. For instance, I was a lecturer back then. I had a lecture on practical applications of digital communications. And what I did, I ordered just a kit of RTL SDRs, and then we had in my lab exercise, then I made the students play around with these RTL SDRs and try to look around the spectrum and try to find out what kind of signal is this in the spectrum. And I was really excited that, say, this rather niche technology that it was up till then became more widespread then.
Yeah, indeed.
Well, when I remember what I
This
did,
is a good development of the history until now.
yeah, I remember what I did back then. maybe you've seen that video from who was it? Someone who was using the USRP1 to emulate a GSM base station. I think about 10 years ago, 12 years ago, something like that. And this guy, Christine Patchett. Well, anyway, that time Chris Patchett was programming a GSM base station. And well, I mentioned earlier here in the stream that I passed my amateur radio license back in 1989, so that's quite some time ago. And that was when I was trained in circuits and oscillators and all those things. And I followed up the development in those past years. And what we've seen, the industry going away from components with a wire at the ends, right? Wired components back to surface mounted devices. And first of all, those surface mounted devices led to a big rupture because many people couldn't do their experiments anymore because soldering was quite difficult, and a lot of electronics engineers or vocational hobby engineers turned away from their hobby and didn't do it anymore because, well, they couldn't keep up with the kind of products, kind of parts you could buy, and they couldn't use them. And and about 10 years ago or so, or 10 to 15 years ago, we saw those breakout boards coming up. And many companies were producing little PCBs with little tin patches, whatever, metal patches, where you could solder up your surface-mounted devices, ICs, and so on. And this brought in a lot of new creative people. And at the same time, well, this is analog electronics, but well, electronics in general. But more or less at the same time, we saw those USRPs coming up. And I think with the USRPs, I personally had the impression that there was going, there was opening a door in front of myself, and I was looking into Wonderland, you know, an entirely new field of research and also hobby activities, and well, which wasn't new after all, but it was new to the public, right? We were able to do things once again, and I was very, very happy about that. I mean, remember last year when we had Professor Rode here in the SDRA, and we had him for a very good reason, because he was one of the inventors, maybe even the inventor back then, who was one of the first people who thought about not working on currents, but on data streams, and the description of an electrical signal. And so, of course, the industry and parts of the academia were able to handle those things before. But since that time, since about 10 years ago, the public and radio amateurs are able to do this. And I also got in contact with GNU Radio, I think, when was that? In 2007, something like that. But in 2006, 7, something like that, I still didn't know, okay, how we're really going to use it, because I didn't see the devices. And I only got to that point when I saw the USR P1, USR P2 coming up, and this was really one of the first really good and really reliable and useful devices where you could generate the signal right out of software, and also process signals directly with software. And this was actually one of the reasons for me that I bought the USR P2. And interesting enough, the USR P2 is still a very, very good system, and very useful, and it helps me quite a lot to do my own experiments. And of course, later on, I mean, every one of us has a whole collection of devices, and of course, we also every one of us tried out the RTL SDR because it's so cheap, and value for money is really fantastic for the small device, and you can do wonderful things with it. And that's also my recommendation to everyone, to start with it, because yeah, sure, I know. So there is a path into software-defined radio for every one of us here, and all the audience who are watching, using these devices that are becoming ever cheaper, like the HackerF and the Lime SDR and the Pluto, Adelm Pluto, and so on and so on. And well, you can have a lot of fun with those devices for sure. So yeah, we have another talk pending.
I should say many thanks to Henning Paul for his both contributions to this conference. And
you're welcome.
So have a nice afternoon. I see you are sitting in a sunny garden, and I would like to sit there as well.
Well, but Michael, you're sitting on a beach.
Yeah, that's my green wall.
Yeah, Henning, a big thanks from me also. We'll have a panel after the next talk, which is the last talk for today and for this year. I'm reading from a studio control that there is a. Oh yeah, perfect. The line is good. Erwin, thanks for coming in. I see you moving, which is very good. The information was just from studio control that the pictures is kind of stand still, but that's good. Okay, perfect. Dear audience, I would like to present Erwin to you. So, Erwin is a Dutch radio amateur with a call sign Papa Echo 3 Echo Sierra. He's been born in 1961 and studied technical physics at the University of Delft, and had a variety of functions with industrial and services organizations. And he now lives in the department Meuse in the northeastern part of France. And his special interests are digital signal processing and SDR. And he's a member of the IIRU Region 1 EMC committee. And he's a voluntary admin for the WhisperNet website and writes articles for the magazines Funkamateur and Viren Electron. And yeah, I hope Erwin and Michael, you know each other. from the Whisper community. Or I'm pretty sure you do.
From Enans.
Okay, very good. So the talk is going to be about a red pitaya for a different purpose, a modern lab measurement equipment that can also be used as a software-defined radio, and the red pitaya STEM lab and SDR lab and their application not only for Whisper and FT8. So as we had it before, we pre-recorded the talk. Dear Studio Control, please go ahead and play our pre-recorded contribution.
In this presentation, I will tell you about the Red Pitaya instrument board as a tool for radio amateurs. Although it was designed as a piece of programmable measurement equipment, with the right software it can be used as a complete software-defined radio as well. My name is Erwin Serlet. I am a Dutch radio amateur living in the northeastern part of France. We live close to Verdun and Metz in the department Meuse, the least densely populated part of France. When we look from our terrace, we see the fields of our neighbors in Maidenhead locator JN28. Before introducing Red Pitaya, we will look at the differences between doing lab measurements and being a radio amateur. We take a look at the base software and make a choice for the main processing platform. The alternative software of Pavel Demin and its multiband receiver capabilities will be shown. We will verify if this radio is up to par. A quick look at the various software used and some alternatives will lead us to the wrap-up of the presentation. To get all energy from our antenna into the transceiver, the impedances should match, and we have chosen 50 ohm as our standard. But if you want to measure a circuit without disturbing it, you want to take as little energy from it as possible. We will see that the two different Red Pitaya variants, STEM lab and SDR lab, take this into account. When using one or the other as a SDR or a multiband digital mode receiver, we will find that there are ways to work around these differences. Red Pitaya is a small Slovenian organization that started to deliver a new kind of lab equipment based on the Xilinx Sync system on a chip in 2013. Small, affordable and completely reprogrammable with open source software. They were an instant hit with universities and in other scientific environments. And this is what they created. A small, bright red printed circuit board with many possibilities to interact with it. At the left hand side we see two input channels and also two output channels. Under the thorny heatsink we find the system on a chip with an ARM Cortex processor plus a field programmable gate array. At the right side there's Ethernet, USB, an SD card and some more options. To interact with the board at various levels, we find a bunch of digital input-output pins, analog input and output, and quite a few bus systems. Let us now take a look at the STEM lab Red Pitaya. all organized around the system on a chip, the Xilinx Zinc. It has two input channels going into an analog digital converter working at 125 MHz. The resulting bit stream is handled in the FPGA ARM Cortex chip. This means that the software on that chip defines what it will do with these measurements taken from the real world. And you can change that software almost on the fly, as it is a field programmable gate array that is doing most of the heavy lifting. Here also the signals that travel via the digital analog converter to the outside world are created. For the rest, it is a single board computer with memory, peripherals and connectors. The SDR Lab variant looks almost the same. Still, there are some important differences. A more powerful system on a chip, meaning more powerful applications. Input channels designed with the radio amateur in mind. The 16-bit analog digital converter, with a sample frequency a bit different from the one of the STEM lab. It is directly related to some important SDR software. And the output channels are also coupled via a 50 ohm radio frequency transformer. Let's look a little deeper. When we take a closer look at the electronic design of the input circuits, the differences between STEM lab, from the lab measurement world, and the SDR lab, tailored for radio amateurs, are striking. For the STEM lab, we see that the input is set up to isolate the whole system from the device under test, like you could find on the bench oscilloscope, for instance. We also see a 10-bit version or a 14-bit version. With the SDR lab, it is quite different. The board is heavily coupled to the outside 50 ohm world and so becomes part of the system via this transformer, and there's almost nothing in between going into the analog digital converter. Now for some quick words on the core of the board, the system on a chip, the Xilinx Zinc. This is a tandem of an ARM Cortex A9. Here you see the 10 version and here the 20 version, paired to a field programmable gate array. With software called Gateware, you can freely program the logic cells and digital signal processing slices of this FPGA to tailor its functions completely to your needs. It makes the board into a real transformer. Whether you need a lab measurement system like a spectrum analyzer, an oscilloscope, a function generator, or a vector network analyzer, all with a click on the GUI that runs in a web browser. But it can also be a software-defined radio, or even a 16-slice multiband receiver. So the software is in control. That software is loaded onto the onboard SD card, and it comes in a few flavors. There are versions for the STEM lab, versions for the SDR lab, and from an external source like Pavel Demin, there are images for the SD card as well. Remember, it's all open source and can be modified by anyone. Starting up the device is quite simple. You download the flavor of the software you are interested in, load it on the SD card, and then the Ethernet connected device is at your command. When you are using the software RedPitaya provides, this is the standard user interface, a web page in your browser. Here you find the lab device you can choose and more functionality that would take another presentation to describe. Mind you, there even is a standard SDR transceiver included with that kind of software already. Now that we have seen the basic device with some of its detail, we can start to think about radios. When we take the StemLab with its Red Pitaya software, we'll already found one SDR application. And we can add 3 more from the marketplace to make the device controllable by Power SDR or HP SDR. The SDR controller software can either use the Hermes or Metis protocol or take control via an XTO DLL file. When these extra programs are installed, the GUI starts to look like this. Here, the central applications, the standard applications that were already there, the StemLab SDR transceiver that was included with the standard software, and the 3 variants that we have taken from the marketplace. And just as an example, I'll show this Power SDR implementation. In the setup screen you can see that it has found an HemLab or StemLab on a specific IP address, and that's the way to connect to it. I could also have used Spark SDR, other versions of OpenHP SDR, Thetis or HD SDR, or GNU Radio for that matter. We see here that we find the radio via its IP address. Now I will show you in real life how this works. The first thing we see here is the Red Pitaya working as a multiband receiver. This is based on the work of Pavel Demin. If I go to the control window, that would be one of the Red Pitayas that I have. And here you see the menu that opens up. I can now change directly from the multiband FT8 transceiver to something else that I would like to do. For instance, use it as an SDR transceiver compatible with HP SDR. When I click this, the FPGA is loaded with a new program, a program that can make contact to the right software, HP SDR software, instead of using the same multiband recorder. When I switch it on, you can see Power SDR open. I've switched to the 80 meter bands because it is quite late at night at the moment. And the lower bands have of course a better signal at this time of the day. What you can see here is one band showing its FT8. And when I push one of the buttons, I suppose it will be heard as well. When we look at the setup, we can see how it is connecting. As I said before, via the Hermes protocol using an IP address, and this is the IP address for my SDR lab, Red Pitaya. Of course we can switch bands, go to another part of the frequencies that we are interested in, or look at more general shortwave bands. Now the question of course is it a good radio? It all depends on what is good for you. I myself am mostly interested in digital modes, and I found that it is a very sensitive, stable and selective radio. But I've also heard it and used it on single sideband, and it works as well there. And for instance, if you go to a PSK reporter and go to the statistics of that page, then you find in the top lists that all these guys use Red Pitaya for spotting FT8. Another way to look at its quality could be the bandwidth and the number of parallel receivers. Do you need or want many receivers in parallel? And what kind of bandwidth do you need to do the things that you like? This all depends on the software that you want to use. And this table gives a good indication of the possibilities. You can go from 6 receivers with the smaller bandwidth to, for instance, with GNU Radio 1 receiver with a 2.5 MHz bandwidth. And there are many different variants of SDR software that you can use. And all these standard applications come with their own functionalities. You might need calibration of frequency if you want to be spot on for whisper, for instance. You might need to have an exact output power, use pre-distortion or diversity, or need, at your situation with a lot of noise, a variety of digital filters. Or maybe you're interested in additional software that you can find via plugins. Now let's look at the real-world situation. I monitor FT8 and Whisper, and the first few days this was the result. It's hard to read, but I had about 116 countries heard in 24 hours. Since then I've optimized a bit, and on April 4, at UTC 22 hours, it was like this. I had 142 countries for the last 24 hours, and over 150 countries spotted in 1 week. And as I said before, you find StemLab and SDRLab users in the top lists on PSK Reporter. So let's take a look at PSK Reporter again. I hear Tasmania, which is not too difficult, as it is in the grey line somehow. Let's look at the statistics here. We are interested in the top monitors by reports over the last 24 hours. Normally you would find me with my in-house antennas somewhere around the bottom. But when we look at all the top monitors, it looks as if they are all using the Red Pitaya for this target, just to be in the top of the FT8 monitoring. All the little things that we can have fun with. Advantages. Some older radios cannot be coupled. For others you need USB, but having Ethernet on board makes many things easier. It's a transport layer not only for controlling the device, but also for the data going in and out of the system. And it is a very transparent solution. Now that we have seen that the Red Pitaya board can quickly be used as a transceiver, it would be nice to flesh the system out a bit. Tailoring the radio to your needs can be done with additional hardware as well as with software changes. Let's look at one of these examples. Let's add a GPS. A GPS module can be added by connecting it to some of the I/O pins I have shown you. How this can be accomplished and what the programmatic needs are is well documented on the Red Pitaya node site of Pavel Demin. The result will be a device that has very stable and precise timekeeping and frequency control. One thing to be aware of is that there are differences in power and signal levels with the different GPS modules that you find on the market. So you have to tailor these to the signal levels that you want to use in connection with the Red Pitaya boards. Another add-on. When I started to use the StemLab board many years ago, I was not really looking at optimizing the performance. I found it amazing enough that the board designed for doing measurements could play radio as well. Later I found an interesting small add-on board that only needed a few additional pieces, like an Arduino, to be pressed into service as a broadband preamplifier. This can even be simplified when I find some time to convert my Arduino sketch to a small Python script running directly on the ARM Cortex of the Red Pitaya itself. When you start using the RF output of the Red Pitaya for other things than Whisper, you will quickly start to think of adding a power amplifier. But then you will also need some extras to switch, transmit and receive, to clean the outgoing signal with the right low pass filter, and possibly add a few circuits in the receive chain as well. And that kind of projects can be found on the internet, like this well-built design by one of my Dutch fellow radio amateurs. Here in the right hand corner you see the Red Pitaya board. It is connected to a PA, probably one of 50 to 70, maybe 80 watt. Here's a whole bunch of low pass filters, a control board, and he even included a small single board computer to control the whole thing. Now, before we come to the conclusion of this presentation, I need to spend a few slides on the software side of things. We can look at it from different angles. For complex but slow processing, we would like to use the Linux ARM processor. It's Linux as operating system, it has shell scripts, Python, C or C++. For the user interface, it is using JavaScript and HTML. The connection from that front end to the back end is run by a web server. And the true digital signal processing is on the field programmable gate array. It's quite a bunch of software to learn. So a good start would be with the Linux-based programs and look how these work together. Like for instance in the multiband Whisper and FTA receivers that can be found in the Pavel Demin software. How do they work together? When you look at the cron files, you find pointers to decode scripts and upload scripts. And the decode script itself reads data from write config files. And you see that in the StemLab FPGA there is a fit in the config files for 8 bands in parallel. But that's not 10 HF bands and the 6 meter that you could also handle. But when you look at the SDR-Lab software, it already handles 16 decoders or receivers in parallel. And then there's also something to do with using different antennas. Wouldn't it be interesting to switch between antennas and switch maybe even over the frequency bands if you're using the StemLab, using higher frequencies during the day and lower frequencies during the night, following the propagation patterns? That's something I've done. I used the base system to add switching between the two RF inputs and setting the frequency bands according to a day and night rhythm, favoring the lower frequencies during the night and the higher frequencies over daytime. As the SDR-Lab can handle all bands in one go, even here the small hardware differences between the two Red Pitaya variants are an advantage. In this presentation I do not have enough time to tell you many things about the instrumentation side of the Red Pitaya boards. But one thing is so interesting to radio amateurs that I wanted at least to include some slides. It's a vector network analyzer. You cannot use this only based on software. You need a little extra hardware. Examples of this can be found on the sites of Red Pitaya or on the site of Pavel Demin or others. You need extra hardware because you also want to measure the reflected power. You could also buy a little add-on from Red Pitaya themselves, which makes it possible to use the Red Pitaya standard boards, both of them, as a VNA. The device under test is connected here. You might be interested in creating the standing wave ratio charts of an antenna or something that I did, create a Smith chart of a low pass filter that you are trying to measure. In this case, a low pass filter for the 30 meter band. Even though the reprogrammable lab measurement device used as a radio is pretty unique, there are some alternatives. If you only want to do receive, there are very simple SDR shields for the Arduino, for instance, from Elector. We are all aware of the famous cheap SDR dongle, or you might already have an SDR player, RSP1A or one of the others. The VVSDR, the RX888 or the older one, the RX666, are all alternatives for receive only. If you also want to transmit, you might think of the Hermes Lite, the self-built Magnus SDR, the Multis SDR, the Lime SDR, there are many more. There's also a tremendous other thing. It is built around the Red Pitaya board, the Charlie 25. The picture you can see here on the right, with all the input and output filtering, and somewhere down there, deep down at the right hand top side, there is the Red Pitaya board. Other alternatives could be FPGA development boards, like the Intel DE10 Lite and the Digilent Basis 3, but that would need some serious FPGA programming done by yourself. So what will happen with this kind of hardware or new SDR hardware in the near future? If you can sample quick, you can make a direct radio without needing an analog mixer as a front end. Or if you go to higher Nyquist zones and use your information theory and filtering smarter, then there are also possibilities with the current versions. Whether these will be taken into new Red Pitaya boards, I don't know. It's time to draw some conclusions. Both Red Pitaya variants offer a stable platform for SDR applications till around 50 to 60 MHz, so inclusive of the 6 meter band. They both offer many opportunities for expansion. But they can also be directly used as a receiver or a transceiver for multiband, digital modes or other modes. And with 2 HF inputs and 2 HF outputs, they offer a lot of flexibility. I find the performance outstanding. Sensitive, selective and stable, even when not using a GPS. As measurement equipment, they can replace a dedicated oscilloscope, a signal generator and a spectrum analyzer, and with extra hardware it even becomes a VNA, a vector network analyzer. Explaining all these things would be something for a different presentation. Even after a few years, these devices give me plenty of headroom for experiments, as well as a fine radio for daily use. Thank you for your attention, and we might even have time to take some questions.
So, Evan, thank you very much for this wonderful talk. And I'm also the proud owner of 3 Red Pitayas. They're also part of my play box, right? My box of tools which I'm playing from time to time, trying out things. And yes, I've also tried out the little preamplifier board. Because I had the honor to do some experiments on, I helped to prepare the first version of the device that went to Antarctica together with Delta Fox 2 November Uniform, Rainer. Well, interesting device, funny little box, and as a radio amateur, you can do a lot of things with it. Yeah, absolutely. Okay, Michael is here also. Now the waves have started to flow again and go to the beach again. So the background is moving and Michael is there. It's good. For sure, there are comments. Michael.
Yeah, thank you very much, Erwin. I think you know a lot of Red Pitaya, so let me ask, are you on the payroll of them?
No, I'm not. But I get a lot of support from them if I have technical questions or need help with something.
Okay.
And yeah, it really appears that SDR is a lot easier than in the past. With things like the Adam Pluto or the Red Pitaya or other boards. It's so much easier, even for simple amateurs like me.
Did you make any measurements on that, or should we explain what Jean-Michel and I discussed in the background in the chat?
Yes, please.
Did you make measurements on the 16-bit Red Pitaya?
What kind of measurements are you looking at, Michael?
Maybe on the effective bits. Well, there is a discussion on what is the effective bits for the 14-bit and the 16-bit system, and Jean-Michel gave some information on his measurements or of his colleague.
No, I didn't do measurements myself, but there is a very interesting article on that in one of the previous Funk amateurs on effective bits in the different setups of analog digital converters.
Okay. So Jean-Michel, would you please repeat what you wrote in the chat?
So we, as part of our Master 2 radio frequency and digital electronic courses, one of our laboratories is to measure the effective number of bits. So basically putting various loads or a coherent, the same signal on the A to D input as the clock signal to measure at the zero crossing or the maximum. And basically the effective number of bits of the 14-bit Red Pitaya is 11.8, give or take. We have not done the measurement on the 16-bit Red Pitaya. I should actually. But some other boards that are based on the same A to D converter clocked at the same 122.88 megahertz claims 12.4 effective number of bits, which is not the expected gain from going from 14 to 16-bit, of course. Plus, additionally, the issue of the voltage reference, which has been discussed on several websites, how to add voltage regulators, because at the moment the A to D converter is a voltage reference on the power supply, which is never done, of course. And the issue of a clock signal, the jitter of the phase locked loop that goes through the FPGA and that will introduce that will degrade performance of 14-bit. These are all conclusions for 14-bit Red Pitaya. They should be extended to the 16-bit. We got a few of them in the lab, but we have not done the measurements. A colleague of mine replaced her optical control link from a 14-bit Red Pitaya to a 16-bit Red Pitaya, expecting much better performance, and also because we're using the undersampling by using the second Nyquist zone, and the improvement was far from the expected. Actually, we had degradation of the performance. So the actual impact on the radio frequency front end, as you've shown, there is no reconstruction filter, there is no anti-aliasing filter, which is very nice when you want to play with the raw A to D information and the undersampling on the upper Nyquist zone. But I'm not completely sure that it doesn't impact the stability of the measurement at the end.
Yeah, okay, thank you. Well,
so actually the 16-bit Red Pitaya, I just complete. it will actually sample up. This is what Erwin was showing at the very end. You can actually sample up to 700 megahertz. The track and hold of the 16-bit Red Pitaya will let you input up to 700 megahertz. After the sync function will really make the signal drop. So sorry for interrupting.
Okay, I can add that I have a little bit experience with the Red Pitaya, and the Red Pitaya will be used in the electromagnetic noise area monitoring system of the DARC, as well as my applications in the Antarctic area, where I use FT8 and the Whisper equipment since several years now. And they work really stable, I could add on it. It's a good idea. And now we have an enamps receiver placed at the Antarctic area to take a good reference for the European measurements, because we expect the Antarctic will be the only continent worldwide where we don't have any VDSL, any power line, and so we expect a very low noise level there.
Yeah, absolutely. Yeah, well, Antarctica is a fantastic playground around there, and someone from around here, from Munich, Teresa, she's currently the radio operator down there, and she's very helpful because she's installing things which she gets from time to time. But now in the moment, of course, it's winter time, and in Antarctica it's completely dark and completely windy and completely cold, very, very cold now. So a very challenging environment anyway, with static charging of antennas and all sorts of funny effects on there. Well, yeah, the Red Pitaya is for sure an absolutely interesting component for radio amateurs, but also for the academia. And I'd like to take this opportunity to lead over to our panel, because we have all the other speakers also around here. And I'd like to throw the ball to you, and I would like to trigger the idea of having the Red Pitaya or other hardware as educational devices in the academia. So, Luca, Christian, are you using the Red Pitaya in your institute?
We are not able to give any information about that because we only worked on our bachelor thesis. But I think that our institute might use it.
Okay, of course, yeah, I know the special background. Okay, but I guess you know it and you're playing around with it. That's good. Henning, what about your institute? Are you working with or have you been working with the Red Pitaya in university environments? Oh, the picture looks a little frozen. This channel doesn't seem so stable. Jean-Michel, another question. Henning, was it you? No. Okay. Jean-Michel, a question to you. You mentioned yesterday, that you're running a laboratory where people can log in and from remote and do experiments and so on. Can you tell us a little more about that environment? How is it with the Red Pitaya, or is it with a different hardware? Or how are you doing that?
We are intensively using the Red Pitaya to answer about the bachelor level and master level. In our sequence at the bachelor level, we remain at the 16-bit microcontroller bare metal C programming, And what the main challenge that we found, and I think mostly everyone is finding with the Red Pitaya, is the wide culture you need to acquire before you can actually completely master the Red Pitaya, from the kernel driver on the Linux side to the library and the user space. So this is where we're promoting the build root environment that gives you a consistent framework on a Linux cross compilation. And then in addition, you need to master the FPGA. In Erwin's presentation, I believe he relied on Pavel Demin's framework, but this means also that you need to understand VHDL Verilog. And at the moment, a colleague of mine who's teaching FPGA explains, and I'm feeling he's correct, that actually FPGA development now is what microcontrollers were 15 years ago, before we had a decent GCC and a decent high-level languages. And it's quite fascinating to see that now FPGA is moving in the open source world. We are getting rid of all these closed source, poor quality software, such as Vivado from Xilinx and the Altera software. We're getting open source synthesizers. We're getting high-level languages, Python description of the HDL workflow. So I think we might expect the same revolution in the FPGA environment than we had in the software for the last 10, 15 years. So that's truly fascinating with the Red Pitaya. So it is a core aspect of our teaching that allows us to wrap in our electronical engineering teaching both Linux, C programming, kernel driver, VHDL, and radio frequency electronics. So it makes really a binding support for all these teaching classes. Yeah.
Yeah, about
this one is actually right in front of me.
Yeah, absolutely. Yeah, about FPGAs, I recently read about a Spanish engineer who recently developed an FPGA programming environment, a very easy one, where you don't need to know VHDL in any of these languages. And I thought this is very, very interesting. But well, I don't have the time to research that now. Well, he said that he might be around at our next SDRA next year. So I'm very much looking forward to that kind of talk. And I see it just in the same way. I mean, unfortunately, I have not had the time to go into FPGAs. I've just seen those contributions in the past. You need a little time to work in those fields, and of course, no one of us can do all those things right at the same time, even though they're all interesting and all challenging and highly interesting, fantastic, insightful, and whatever. But nevertheless, I also think that FPGAs are an interesting playground. And they offer a lot of development also for the entire SDR field. Yeah, and the Red Pitaya being a quite a good market cheap device, which almost everyone can afford, is certainly a good playground for that also. Luca, Christian, did you in your general instruction in your university career, did you have the chance to work with FPGAs?
Yeah, I want to comment on that. I have planned to work with an FPGA in summer. I will try to use an FPGA with the software RFNOC to implement in software-defined radio.
Okay, very interesting. Henning, how's FPGA training at the University of Bremen? How do they do that there?
Well, I don't know how it's currently done because I left university 3.5 years ago. But back when I was a student, we had a lab on FPGAs, which was mandatory for both communication technology students as well as digital technology students. Yeah, but
maybe I think, Henning, it was Stefan Wolter who was a professor. Was he?
when I had these courses, that was well earlier already. That was around 2003 or 2004. I
Okay.
had these courses. Yeah.
Yeah, I know Stefan because Stefan is a colleague of mine, and he teaches VHDL in one course for the 6 semesters in at Hochschule as well. Yeah.
Yeah.
So, and I know that he made the course at the university as well.
Oh, now I've got it. Yeah. Okay. Sorry to interrupt you. Go ahead.
Yeah. Yeah. So I did a little bit on FPGAs, but I actually learned it when I had to use it for my for a master, say, diploma project back then, where I implemented a beamformer in our 8-channel multiple antenna system. Basically, the idea was to do the phase rotation in hardware and the FPGA, the complex multiplication, and then upload the signal only once, because you saw that in the talk, 8 channels, only USB 1.1, so means you won't only upload the data once and then only.
Sound is gone?
Yeah,
That's
maybe
that
he
is
has a Wi-Fi.
No,
garden
So,
effect.
Sim is back. Say the last sentence again, please.
So the idea was just to have a different phase rotation factor for each of the channels, and then upload the signal only once, and then have it phase rotated in hardware in the FPGA. So this was my project back in 2005 when I joined the department. Actually, my internet connection is it's interesting because YouTube works flawlessly, but I guess this is UDP what the tool is using, and I have 2 open WRT routers in the hop in between, and somehow they seem to swallow some of the UDP packets. So it's interesting because I don't have any problems with, say, plain TCP connections.
Okay, very good. So in the meantime, I researched and I found that message that contained that information, and yeah, that's from the Tangerine project mailing list, and it says that's a project by Pau Gomez Cabelca, who is a PhD student at the Photonic Institute of Barcelona. And he programmed something called Canvas, and it's a free graphical DSP design tool that requires no HDL or FPGA knowledge. And he further writes that first the user makes a DSP drawing with a graphical design tool which is based on an add-on package for LT-Spice. The drawing is then sent to a remote server where VHDL code is generated and sent back to the user. And finally, the code is configured and loaded onto a Redpitaya StemLab 12514's FPGA over SSH via Ethernet connection. And Canvas also allows for changing the configuration of the DSP circuit, meaning the user can tune in real time. This makes Canvas a great tool for rapid prototyping your DSP on Redpitaya. And if you're looking to get started with using Canvas, you can read more about it on Pau's website and check out the project on GitHub. There you find a detailed wiki with instructions how to prepare your Redpitaya, install Canvas on your PC, register to the remote server, configure both LT-Spice and Python GUI, as well as tutorials with some example use cases. And the website which I'd like to give here is www.dspsandbox.org/ now capital C Charlie, capital Charlie, Canvas. Canvas written with a capital C at the beginning and a / at the end. That's the that's the address. Maybe you can look it up and Google it. Well, enter it directly in your browser, because I think this is really an interesting approach, and I figure out it could also become an interesting tool for for teaching? Well, as I said before, yes, FPGAs are interesting, and there is a lot of potential still with FPGAs, and so teaching FPGAs is for sure an interesting and important field of activity. Evan, did you program FPGAs up to now in the past?
No, I only did some of the examples that I found on the internet because it is really a steep learning curve before you are able to get the whole tool chain stable, because it depends on a lot of variables like versions of the control software that you use. It is quite. I found it quite difficult.
It's a horrible
so-
mess, yes.
So with me, and you need some time to do it, and I mean, students like you, Luca and Christian, you have probably enough time.
Time enough.
Whereas at least when I was a student, I had enough time. I don't know if today's students have so much time, but with the they don't. Okay, Bologna process makes it impossible, right? And you have trimesters anyway, which makes it even more challenging. Okay. Well, that's a very interesting field that will accompany us also in the next years. And I very much hope that next year we will have a special section on FPGAs, and hopefully some more introductory talks, and maybe also kind of a tutorial to play around with FPGAs. So, okay. Time is quite late now. We're going very boldly towards 18 hours, and there is still an evening which you might want to enjoy with a beer in the garden. So Henning, I see you're sitting in the garden already, and I see through the window that the sun is shining. So this year's Software-Defined Radio Academy is more or less coming to an end, and I'm having a last look into the chat. There are still 42 followers, 42 people listening to the chat or listening to the stream, which is quite a big number at the end of a Sunday afternoon, and I'm proud that we were able to give so interesting input to so many people in these 2 days. And generally, let me thank you all for contributing, for joining, for coming in, and sharing your ideas, sharing your thoughts, sharing your experiences, because this is what makes the SDRA an interesting platform. And I would like to thank a number of people. First of all our speakers, because the speakers are those who make the SDRA possible. Without the speakers, we couldn't exist. Then the organization partners, particularly Jean-Michel and your colleagues from the GNU Radio Days, and also our video team. You can't see the video team. Short request to the video team. Can you switch the other camera on and give some insight on how it looks like in here? Is that possible? Yeah, over there. This is the video team.
Yes, of course it is.
Okay. So you see to the left, this is Torben. Torben is controlling the vMix channels where the speakers come in. Mark in the middle is controlling the audio channels, and Sebastian to the right is the master controller who is interfacing with me and responding to all sorts of background comments and messages, and who is supporting me with everything so that I don't need to do that, and keeping a lot of work from me because I'm busy with talking to you. So, our team has made this possible. My tremendously, incredibly big thank you to you guys, because it was an absolute pleasure working with you, and you've made this possible. Thank you very, very much.
Great
Thumbs up. Excellent. Okay. So we're at the end of this year's SDRA. Most of you are at home. Well, for Luca and Christian, I think this pretty much looks like a university room or something like that. And I don't know how far you have to go to be at home. I think it's a campus there. Nevertheless, thank you, everyone. Have a good journey home if you need to travel home. And otherwise, have a nice evening and enjoy the evening beer. And we're going to see you again next year. Thank you very much.
Yeah,
Michael,
I just want to. I think I should add something of the day, what happens today, and as I feel we have two parts in the afternoon where we saw that we are not focusing with the SDRA only on the hardware, but also going from over the software up to the spectrum evaluation. This was a big part, and it was so big the first time in SDRA. So it shows that what is the development of the SDRA, and we expect a little bit more, as you were talking before, Markus. I think we expect in the next future a little bit more on that part. So not to top your words, just to add this special view. And of course, thank you all. Great.
Oops. Yes, thank you also. Yeah, that's of course an interesting comment where we're going. We to build topical blocks, which is an interesting development, and yeah, I think this is simply the way we're going, and I'm looking forward to see which topics we're getting in next year, and I'm very much looking forward to the next SDRA in 2022.
Important one organizational behavior. We had some talk on the chat, and they were asking, what about the talks? Could they be provided at the channel? Yes, we will cut them into small pieces of the talks, and they will be provided on the channel. So have a look in the near future. It may take some weeks, but they all will be copied on the channel there, and you will find them there.
Yes, absolutely. Yeah. So in the moment we have a bit over 100 contributions there, and I'm going to. Well, we are going to have all those talks here also. I didn't count them right now. I think 16 or 17 talks, and they're going to be here in a couple of weeks, 2 to 3 weeks, something like that. What I'd expect. Yeah. Thanks to our team, our video team.
So this was my last intervention. Now I say thank you very much to all of you. Have a nice evening and see you the next year.
Yeah, for me also, thank you very much and see you next year. Bye-bye.
Bye.